If 95% of the cosmos hides behind a curtain of darkness, what marvels will emerge when we finally lift the veil? As dark energy silently accelerates the universe's expansion, can human curiosity stretch far enough to grasp the secrets racing away from us? For a moment, picture the night sky above you. Thousands of stars shimmer against a velvet blackness. Each tiny light is a distant sun, and between them lies a vast darkness. In those dark stretches, we often imagine emptiness, but the black canvas of space is far from empty. Beneath the visible tapestry of stars and galaxies, the universe holds secrets invisible to our eyes. The starlight we see, the glowing gas clouds and brilliant galaxies, is only a small fraction of all that exists. The rest is hidden, made of mysterious substance and energy that neither emits nor reflects any light. It's as if an unseen cosmic web underpins everything we can see, an invisible scaffold holding galaxies together and guiding their motion. Take our own Milky Way galaxy, for example. We see its hazy band of light arching across the sky, a multitude of stars bound together by gravity. But observations suggest that the luminous stars and swirling nebulae are just the tip of a much larger structure. Enveloping our galaxy is a vast, dark halo of matter that we cannot observe directly. This dark halo extends far beyond the Milky Way's visible disk, holding the galaxy together in its gravitational embrace. Scientists now believe that only a small portion of the universe is made of the familiar matter that shines or that we can touch. The planets, the stars, the gas and dust, everything we think of as material, comprises less than 1/5 of all the matter out there. The rest is some form of invisible matter, aptly called dark matter. And as if that were not enough of a mystery, an even larger share of the cosmos is made up of something stranger still, an unseen force that seems to be pushing the universe to expand faster and faster. They call this force dark energy. Even though dark matter and dark energy are invisible and untouchable, we know of their existence through their effects. Dark matter's gravity quietly pulls on stars and galaxies, while dark energy's pressure gently stretches the fabric of space. Together, these unseen influences dominate the cosmos. If you could weigh the entire universe, all the shining stars and glowing galaxies would account for only a small fraction of the total weight. The vast majority of the weight comes from these dark, hidden components. It is a profound and humbling realization. Most of our universe is, in a very literal sense, invisible to us. As we gaze up at the night sky, almost everything that truly governs the cosmos is something our eyes cannot see. This notion might sound unsettling or wondrous, or perhaps a bit of both. It reminds us that the universe still holds deep mysteries, waiting quietly in the dark. In this gentle journey, we will explore that unseen side of the universe. We will delve into the story of how scientists discovered evidence of this invisible matter and energy. Our path will take us from the first subtle clues that something was missing, to the dramatic revelations in galaxies and clusters, and finally toward the mysterious force that shapes the universe's fate. Relax and float along as we venture into these cosmic mysteries. Imagine drifting through space, passing bright stars, and slipping into the silent, dark spaces between. There, in the calm and quiet void, we will find hints of an invisible presence that binds and propels galaxies. With a slow and steady pace, let us begin to unravel the story of the hidden universe. Decades ago, long before the term dark matter was widely known, a few perceptive scientists caught hints of something peculiar in the cosmos. In the early 1930s, a Dutch astronomer named Jan Oort studied the motions of stars in our Milky Way. He paid close attention to how fast those stars moved out near the edges of the galaxy. To his surprise, they were moving faster than expected, as if feeling the gravitational pull of far more mass than what was visible in the stars and gas around them. It was as though an unseen mass was tugging on these stars from the dark, helping to hold them in orbit. Around the same time, across the world in California, another astronomer named Fritz Zwicky was observing an enormous cluster of galaxies far beyond our own. This cluster, known as the Coma Cluster, held thousands of galaxies bound together by gravity in a vast swarm. Zwicky measured the speeds at which those galaxies were moving, orbiting around the cluster's center. What he found was astonishing. The galaxies were cruising so rapidly that, according to the laws of gravity, the cluster should have been flying apart. There simply wasn't enough visible matter, the stars and gas in those galaxies, to hold everything together at the speeds observed. Zwicky scratched his head at this cosmic conundrum. The only way to explain the cluster's stability was to assume that there was a great deal of hidden mass providing the extra gravity needed to keep it intact. In a bold leap of insight, he proposed that the cluster contained what he called dunkel materia, German for dark matter. This dark matter, he suggested, was an invisible substance permeating the cluster, far outweighing all the luminous matter that we could see. It was a startling idea, that there could be more mass lurking in space than all the stars and galaxies that shine. If Zwicky was right, the bright galaxies in the Coma Cluster were like leaves floating on a pond, and an unseen water of dark matter was buoying them up, carrying them in its current. His calculations hinted that this invisible matter might be tremendously abundant, perhaps dozens, even hundreds of times more mass present than the visible matter. In the 1930s, such an idea was truly radical. Many of Zwicky's fellow astronomers were skeptical, or simply didn't know what to make of it. After all, how could there be so much matter that no one could see or detect with any telescope or instrument of the time? For a while, Zwicky's discovery lingered at the fringes of scientific discussion. It was a tantalizing clue, filed away under mysteries to be explained later. The science of that era had other pressing puzzles and exciting discoveries, the nature of galaxies, the expansion of the universe itself, that took center stage. Dark matter, as Zwicky envisioned it, remained a shadowy hypothesis without further proof. Yet those early clues were not entirely forgotten. Now and then, other astronomers noticed hints that seemed to echo the same mystery. Over the years, improved telescopes and surveys of stars offered suggestions that our own galaxy might hold hidden mass as well. These observations were like gentle whispers from the cosmos, hinting that something unseen was out there, influencing the movements of stars and galaxies. Still, decades passed without a definitive answer. Astronomers continued to catalogue galaxies and measure their motions. Technology advanced. By the mid-20th century, we could observe stars and gas with far greater precision. As the data accumulated, the stage was quietly being set for a new revelation. The cosmic mystery that Zwicky and Oort had glimpsed in the 1930s was about to resurface in dramatic fashion. Imagine the sense of curiosity and quiet anticipation that must have built over those years. Those scattered clues, like pieces of a puzzle, waited patiently for someone to assemble them into a clearer picture. Eventually, in the latter half of the century, attention would return to this problem of the universe's missing mass. And this time, the evidence would speak so clearly that it could no longer be dismissed or set aside. In the late 1960s, the mystery of the missing mass took a pivotal turn on the scale of individual galaxies. Picture a majestic spiral galaxy, like a colossal pinwheel made of billions of stars. According to what we knew of gravity, most of the galaxy's mass should lie in its bright central regions, where stars are densely packed. Out in the far-flung spiral arms, the starlight thins out, and we would expect the gravitational pull there to be weaker. Just as planets farther from the Sun orbit more slowly due to the Sun's diminishing gravity, so too should stars, at a galaxy's edge, orbit more slowly around the galactic center. Astronomer Vera Rubin, along with her colleague Kent Ford, set out to test this expectation. On many clear and tranquil nights, Rubin studied the Andromeda Galaxy, our nearest large galactic neighbor, and other spiral galaxies, carefully measuring how fast stars and clouds of gas were moving at various distances from each galaxy's center. They used sensitive instruments to observe the subtle shifts in the starlight's frequency, shifts that reveal the speed at which those stars and gas clouds are rotating around the galaxy. Each observation was like listening to the quiet music of starlight, with tiny changes in pitch revealing the speed of the star's dance. What Rubin and Ford found was startling. Instead of the outer stars moving more slowly than those in the interior, the stars in the outskirts were moving just as fast as stars closer to the center. The expected drop-off in speed simply wasn't there. If you plotted the rotation speeds on a graph from a galaxy's core out to its edge, you wouldn't see a downward slope. Instead, the line would stay high and nearly flat. In other words, the stars in the far outer regions were orbiting at speeds that defied the predictions of conventional gravity based on the visible matter alone. This was no small discrepancy. A star on the rim of a galaxy might be moving so quickly that, if only the visible matter's gravity were at work, it ought to break free from the galaxy and drift off into space. But that wasn't happening. Those outer stars remained securely bound in their orbits. The only reasonable explanation was that something else, some additional unseen mass, was present in the galaxy, providing the extra gravity needed to keep those fast-moving outer stars from flying away. That something was the unseen dark matter halo enveloping the galaxy. One by one, galaxy after galaxy told the same story. Our own Milky Way, when studied in detail, also showed this unexpected pattern of rotation. It became increasingly clear that every galaxy was embedded in a vast halo of invisible matter. The bright portion of a galaxy, the stars, gas, and dust that we can see, turned out to be surrounded and surpassed by a much larger dark component. Think of a glowing lantern on a dark, misty night. You see the lantern's light, but perhaps not the clear glass globe that encases the flame. Yet the glass is there, shaping how the light shines and protecting the flame. Similarly, the bright stars of a galaxy illuminate only the innermost regions of a much larger dark matter halo that extends well beyond the visible edge. That halo's gravity influences everything, even though it emits no light of its own. For Vera Rubin and her colleagues, this evidence transformed dark matter from a curious, fringe idea into a central tenet of modern astronomy. The missing mass that Fritz Zwicky had calculated in distant galaxy clusters was not a fluke or an isolated case. It was a ubiquitous feature of galaxies everywhere. In silence and invisibility, dark matter dominates galaxies, outweighing the visible stars and gas by several times. The cosmic dance of stars, it turned out, was being choreographed not only by the stars' mutual gravity, but by an invisible partner holding their hands. Some scientists did consider whether the laws of gravity themselves might behave differently on the grand scales of galaxies. An intriguing idea that could potentially explain the unexpected rotation speeds without invoking hidden mass. They proposed modifications to Newton's laws, wondering if gravity might fall off more slowly than expected at large distances. But as more and more data poured in, those alternative theories struggled to account for all the observations without becoming contrived. The simpler explanation, that each galaxy carries an invisible load of dark matter, fit the data consistently across the board, from small galaxies to large ones. It elegantly and quietly answered the mystery of the fast stars. By the 1980s, the flat rotation curves observed by Rubin and many others had convinced most astronomers that dark matter was real and abundant. The conversation had shifted from asking, "Does dark matter exist?" to, "What is dark matter made of?" That question remains unanswered to this day, adding to the intrigue that surrounds this cosmic mystery. Imagine yourself drifting at the edge of a spiral galaxy, amidst a sparse scattering of distant stars. All around you is the quiet darkness of space. You feel the galaxy's gravitational pull, but you also sense something else, a vast, encompassing presence that tugs on you from every direction. This is the dark halo, an enormous, unseen ocean of mass in which the galaxy swims. It holds you in orbit just as firmly as the bright core of stars does. You are, in essence, immersed in a massive, invisible cloud that shapes the galaxy's fate. The realization that our universe contains such hidden matter was a watershed moment. It meant that the familiar cosmos of stars and galaxies was just the surface of a much deeper reality. Yet, even as this understanding took hold, it was not the end of the story. More clues were on the way, clues that would show dark matter's influence on scales even larger than individual galaxies, and through phenomena beyond just the motions of stars. The next hints of the invisible universe would come from gravity's subtle tricks, such as the bending of light, and from the behavior of matter in colossal structures like clusters of galaxies. Gravity has another subtle way of revealing what our eyes cannot see. In the deep stillness of space, a beam of light traveling from a distant galaxy can be bent and rerouted if it passes near a massive object, much like a river's flow is diverted by a large rock. Einstein's theory of general relativity teaches us that mass curves the very fabric of space, and light follows those curves. Thus, a massive galaxy or cluster of galaxies can act as a gravitational lens, bending the light of objects behind it, and sometimes creating ethereal smears or even multiple images of a single distant object. Astronomers have observed this phenomenon in many places. Imagine looking at a faint galaxy that lies far behind a closer cluster of galaxies. Instead of a single pinpoint of light from that distant galaxy, you might see its glow stretched into an arc, or even split into several distorted reflections around the nearer cluster. These distortions are called Einstein rings and arcs, the telltale signatures of gravitational lensing. They appear as beautiful, delicate shapes in the sky, like cosmic mirages that hint at a massive presence in the foreground bending the light. By studying those distorted rings and arcs, scientists can deduce how much mass lies in the lensing object and how that mass is distributed. The logic is straightforward. The more mass in the intervening object, the more strongly it will bend the light passing by. Time and again, when researchers apply this analysis to massive clusters of galaxies, they encounter the same mystery Zwicky did so many years ago. The visible galaxies and hot gas in a cluster cannot account for the degree of light bending observed. The gravity required to create those dramatic arcs and rings is several times greater than what all the ordinary matter in the cluster could produce. The implication is clear. The remaining gravitational pull is coming from dark matter. Once more, dark matter makes its presence known not by emitting light, but through gravity's gentle tug on the light travelling past. One particularly dramatic cosmic spectacle provided a convincing view of dark matter in action. This occurred when two galaxy clusters collided in a gigantic merger event, a system known as the Bullet Cluster. In that event, astronomers had a rare opportunity to map out the mass distribution by using gravitational lensing like a cosmic X-ray, peering through the chaotic collision to see where the mass ended up. The cluster's clouds of hot gas, which show up brightly in X-ray observations, had slammed into each other and slowed down, piling up near the center of the impact region. However, the majority of the mass did something very different. The gravitational lensing maps revealed that most of the mass from each cluster passed straight through the collision, hardly interacting at all. It separated from the slowing gas clouds and kept on going. In the aftermath, the bulk of each cluster's mass was found in two clumps that had moved ahead of where most of the ordinary gas had stalled. It was as if two ghosts walked through each other, leaving their luminous cloaks, the hot gas clouds, tangled together in the middle, while the invisible bodies continued on. This observation provided direct and striking evidence that dark matter is indeed a distinct component of these clusters. It interacts via gravity, but not through light or the kind of collisions that affect ordinary matter. The dark matter halos of the two colliding clusters simply passed through one another, while the normal matter, the gas and stars, experienced friction and drag. Beyond individual clusters, the influence of dark matter extends to the grand architecture of the cosmos itself. Galaxies are not scattered randomly through space. They form a vast cosmic web, with filaments of matter stretching across hundreds of millions of light years. The prevailing theory is that this web's basic structure was sketched out by dark matter long ago, in the early eras of the universe. In the young universe, dark matter began to clump under its own gravity, forming a loose framework, a network of filaments and knots of invisible mass. Ordinary matter, made of atoms, was drawn in by the gravity of this dark framework and flowed along the same patterns, like dust settling into the grooves of an unseen sculpture. Over billions of years, that ordinary matter cooled and coalesced into stars and galaxies, lighting up along the densest clumps of dark matter. Thus, the cosmic web of galaxies that we now observe is thought to trace the outlines drawn by dark matter's gravity, much as dew on a spider's web reveals the web's form at dawn. The galaxies are like sparkling beads on invisible threads of dark matter that weave through the universe. Today, scientists can even map some of these invisible structures by observing their gravitational effects on light. Through large surveys and sensitive telescopes, they measure the subtle distortions in the shapes of countless distant galaxies, a method known as weak gravitational lensing. By combining these observations, astronomers can infer where mass is concentrated on colossal scales. The resulting maps show clumps of mass where clusters of galaxies reside, and even hint at the faint, wispy filaments of dark matter stretching between those clusters. These maps allow us to visualize, indirectly, the unseen mass of the cosmos. They reveal a universe woven of light and dark, the familiar shining galaxies strung along gossamer strands of gravity. It's a breathtaking concept. We are beginning to perceive the invisible scaffold of the universe, charting an unseen landscape that underlies all the visible stars and galaxies. By now, multiple lines of evidence all point to the same conclusion. From the way galaxies rotate, to the motions of galaxies within clusters, to the bending of light across space, it is clear that the majority of matter in the universe is dark and mysterious. This dark matter neither emits nor absorbs light, and it interacts with ordinary matter only very weakly, apart from its gravitational pull. We find ourselves confronted with the fact that everything we have ever seen, stars, planets, nebulae, even ourselves, is only a small fraction of what's out there. The rest is this shadowy substance, perhaps made of some as yet unknown type of particle. Despite the strong evidence for its existence, dark matter itself has not been directly detected on Earth. It remains, for now, an elegant and haunting explanation for cosmic phenomena, a substantial presence that we know is there but cannot yet touch. For a time, scientists wondered if perhaps this dark matter could simply be ordinary matter, hiding in unusual forms. Could it be made of countless faint, undetected stars, sprinkled through the galactic halos, or vast clouds of cold, invisible gas? Might it be a multitude of small black holes, each too isolated to notice? Over the years, studies have largely ruled out these familiar possibilities. The invisible mass seems to be something fundamentally different, likely a new kind of particle or exotic substance that does not shine or interact in any familiar way with light. In essence, it is a ghostly component of the universe, present in enormous quantities, yet so diaphanous in its interactions that it eluded direct detection for decades. Discovering its true nature remains one of the great quests of modern science, a quest that continues quietly in laboratories and observatories around the world. One might think that uncovering this immense amount of unseen matter would mark the climax of our tale of cosmic mystery, but the universe had another surprise in store. In the late 1990s, as astronomers were studying distant exploding stars called supernovae to measure the universe's expansion rate, they found something astonishing. The expansion of the universe wasn't slowing down as everyone expected. It was speeding up. The distant supernovae appeared dimmer and farther away than they should have been in a decelerating universe. It was as if some unknown force were pushing the fabric of space outward, overpowering the pull of gravity on cosmic scales. To explain this unexpected acceleration, scientists proposed another invisible component of the cosmos, which they named dark energy. This dark energy seems to permeate all of space, driving galaxies apart and stretching the very fabric of the universe. In contrast to dark matter, which pulls things together with its gravity, dark energy produces a repulsive effect, acting like a subtle pressure built into the universe that makes space expand faster over time. The concept was radical, yet it fit the observations. It was as though the universe, in its old age, had turned on a mysterious fuel that accelerates its growth. The emergence of dark energy as an idea was a profound shift in our understanding. It suggested that the invisible content of the universe comes in two forms, each dominating over the visible in its own way: the gravity-binding dark matter and the space-stretching dark energy. According to the best measurements, dark energy is even more prevalent than dark matter. In fact, it appears to constitute roughly 2/3 of the entire cosmic energy budget. Dark matter makes up most of the rest, around 1/4, and the ordinary matter we know, all the stars, galaxies, gas, dust, and life, accounts for less than 5%. In other words, everything we find familiar is just a thin glaze on a vast cosmic ocean of the unknown. The universe, it turns out, is ruled predominantly by the unseen. Our journey so far has taken us through the discovery of dark matter, the hidden mass that quietly binds galaxies and clusters together. Yet, the story of the invisible universe is not complete without exploring dark energy, the mysterious force that is shaping the cosmos on the largest scales. Drifting here, at the threshold of understanding, we can feel both wonder and humility. The cosmos has revealed itself to be far more strange and magnificent than we ever imagined. Each answer we uncover about the universe's invisible components seems to open new questions, like doors leading deeper into the unknown. As we float in the calm darkness of contemplation, we realize that in the face of such cosmic mysteries, our own knowledge is small, and that is a beautiful, humbling truth. And so, we prepare to venture onward. In the next part of our journey, we will continue this gentle exploration, turning our attention to that enigmatic dark energy. With the same relaxing, unhurried pace, we will listen as the universe whispers to us about the force that is driving space to expand. The story of the unseen cosmos continues, and we will follow it further into the darkness, curious, calm, and open to whatever secrets the silent, invisible universe will reveal next. Far beyond the reach of any telescope, in the silent depths of space, an immense structure unfolds in darkness. There are no signposts or boundaries out here, only the faintest glimmers of distant galaxies, arranged in an almost ghostly pattern. They cluster in chains and knots, as if linked by invisible threads. In truth, they are. These galaxies trace out the cosmic web, an intricate network of filaments woven across the universe. In the black voids between, scarcely any matter can be found at all, while along those hidden filaments, galaxies gather like morning dew on the strands of a spider's web. On these colossal scales, the universe reveals a clear pattern. Filaments of matter stretching tens of millions of light years, intersecting in glimmering nodes where entire clusters of galaxies collect. Between the filaments are vast cosmic voids, sparsely populated realms of near-nothingness. Along the filaments, gravity guides the flow of matter. Diffuse gas streams inward, fueling the birth of stars in galaxies nestled on the threads. The galaxies themselves drift along these bridges of matter, drawn into groups and massive clusters at the junctions. What emerges is the largest structure known, a cosmic web that spans the observable universe, its strands invisible, yet overwhelmingly present. Yet this vast web is almost entirely hidden from our eyes. The luminous galaxies outlining it are merely lanterns tracing a greater presence, dark matter. This mysterious substance, making up roughly 85% of all matter in the cosmos, does not shine or reflect light. It moves through space like a ghost, unseen except for its pull of gravity. Dark matter's gravity is what shapes the cosmic web, drawing gas and galaxies into filamentary rivers and holding the universe's scaffolding in place. Without this invisible framework, the visible matter, the stars, gas, and dust we observe, would be scattered randomly, and the elegant cosmic web would disintegrate. Over time, scientists came to realize that dark matter is the key architect of this vast design. Long ago, in the universe's youth, dark matter began pooling under its own gravity, forming a loose skeleton of filaments. Ordinary matter, the hot gas that would later cool to form stars and galaxies, was drawn into dark matter's deep gravitational wells, like dust settling on an invisible framework. As eons passed, galaxies took shape at the densest intersections of dark matter, and chains of galaxies formed along the dark filaments. What started as tiny ripples after the Big Bang evolved into a cosmic web, guided quietly by the hand of dark matter. For a long while, the cosmic web was largely invisible, predicted by theory and hinted at by galaxy surveys, but rarely seen directly. That has started to change. Astronomers have begun capturing the faint glow of gas strewn along intergalactic filaments, using powerful telescopes and hundreds of hours of exposure. And in a remarkable recent achievement, they even detected the gravitational imprint of dark matter hanging from those filaments. By analyzing how the light of distant background galaxies is subtly distorted, a trick of gravity known as weak lensing, scientists mapped dark matter threading through a gigantic cluster of galaxies, tracing out cosmic web strands that would otherwise remain unseen. Piece by piece, the hidden scaffolding of the universe is being revealed, confirming that the cosmic web is not just a figment of simulations, but a real structure shaping how galaxies are arranged. Our own galaxy is a part of this cosmic web as well. The Milky Way, along with its neighboring companions, drifts within a local filament that feeds into the Virgo cluster, which itself is one lobe of an even greater supercluster known as Laniakea, meaning immeasurable heaven. From our tiny perch inside this grand lattice, we cannot see the full web around us, but we are embedded in it. Every galaxy and cluster we observe is following paths dictated by this unseen cosmic architecture, like leaves carried along invisible currents in a vast, dark sea. Gazing at the cosmic web invites a profound question. What are these invisible filaments actually made of? We see the effects of dark matter on grand scales, yet the substance itself remains a mystery. To truly understand the unseen universe, we must peer closer into the microscopic realm of particles and forces. Somewhere in that shadowy domain hides the identity of dark matter, the very stuff forming the cosmic scaffold. Scientists have been on a long quest to unmask this substance, to discover what kind of particle or object or exotic phenomenon could account for the massive, unseen matter holding the galaxies together. Dark matter earned its name because it neither emits nor absorbs light, making it effectively invisible. It isn't composed of ordinary atoms or glowing gas, or else we would have detected its light or shadows by now. The concept emerged from puzzling observations. In the 1930s, astronomer Fritz Zwicky noticed that galaxies in the Coma cluster were moving so fast that they should simply fly off into space unless an unseen mass was binding them together. He called this missing mass Dunkel materia, or dark matter. Decades later, in the 1970s, Vera Rubin measured the rotation of spiral galaxies and found their outer stars circling the galactic center at unexpectedly high speeds. According to Newtonian gravity, those stars should have flown away into the void, yet they remained bound, again hinting at a vast halo of invisible matter enveloping each galaxy. Further evidence piled up. The way massive galaxy clusters bend background light, gravitational lensing, shows far more mass than what's visible. Occasionally, clusters of galaxies are observed slamming into each other, as in the striking bullet cluster collision. In that event, careful observations revealed that the hot gas from the colliding clusters, which emits X-rays and thus is visible, separated from the bulk of the gravitational mass. The gravity, mapped by lensing, stayed with material that passed straight through the collision. The visible gas was left behind, but something invisible carried most of the mass through. This phenomenon is hard to explain without dark matter. Yet another line of evidence comes from the whisper of the early universe, the cosmic microwave background. Tiny fluctuations in that primordial light, observed in satellite maps, match the pattern expected if about 5/6 of the matter is invisible. All these observations, from galactic scales to the largest cosmic structures, point to the same conclusion. Something massive and unseen is everywhere, gravitationally sculpting the universe. So what could dark matter be, if not the usual atoms and molecules? The leading idea for many years was a new kind of fundamental particle, one that interacts so weakly with normal matter that it has escaped detection so far. Physicists dubbed this hypothetical particle the WIMP, short for Weakly Interacting Massive Particle. A WIMP, perhaps born in the hot cauldron of the Big Bang, would drift through stars and planets without a trace, making it an ideal dark matter candidate. For a long time, WIMPs fit the story neatly. They could have the right mass and properties to explain the amount of dark matter inferred today, and theories like supersymmetry even predicted their existence. But as experiment after experiment came up empty-handed, WIMPs have started to fall out of favour. Scientists have grown more open to alternative possibilities. Perhaps dark matter is not a single species of particle at all, but could consist of something more exotic, or a mix of things. Among the leading new candidates is an ultralight particle called the axion. Axions were first proposed in the late 20th century as a solution to a subtle puzzle in quantum physics, the strong CP problem in the theory of the strong force. But they turned out to be promising dark matter contenders. If axions exist, they would be extremely light, possibly billions of times lighter than an electron, and they would interact with matter even more weakly than WIMPs do. Vast numbers of axions could have been created in the early universe, like an invisible sea filling all of space. Though each axion carries only a minute mass, together they could add up to the hefty dark matter budget of the cosmos. Crucially, axions would hardly ever bump into normal atoms, making them essentially invisible. Physicists are now hunting for subtle signs of axions, for instance by using strong magnetic fields in special instruments to see if axions can turn into faint photons, or by listening for tiny oscillations they might cause in microwave cavities. So far, these experiments have not found a definitive axion signal. But the search is only just beginning. Another possibility is a kind of stealthy neutrino. We already know about ordinary neutrinos, ghostly particles that stream through our bodies and the Earth by the trillions each second, barely interacting. But those familiar neutrinos are far too light to account for dark matter. A heavier, still hypothetical cousin known as a sterile neutrino has been suggested as a dark matter candidate. Sterile neutrinos would interact with other matter only through gravity, making them extremely difficult to detect. If they exist in large numbers, they could contribute significant unseen mass. However, like axions, sterile neutrinos remain speculative, with no confirmed detections so far. In a more dramatic twist, some have proposed that dark matter might not be particles at all, but rather an enormous population of primordial black holes. These would be black holes formed in the first moments after the Big Bang, perhaps from rare, ultra-dense clumps of energy that collapsed under their own gravity. Unlike black holes born from stars, primordial black holes could span a wide range of sizes, potentially including some much smaller than the Sun. Being black holes, they would emit no light, thus acting as dark matter. For a time, this idea seemed intriguing. Countless unseen black holes drifting through galaxies could gravitationally explain the missing mass. However, Extensive searches for the gravitational effects of such black holes, for example, their bending of starlight as they pass in front of background stars, have so far found no sign that enough of them exist to make up all of dark matter. It appears that while primordial black holes might exist in certain mass ranges, they cannot account for the bulk of the dark matter without contradicting observations. A further avenue is that dark matter could be multifaceted. Instead of one new particle, there might be an entire dark sector, a suite of different particles interacting with one another via forces we don't directly sense. In this scenario, dark matter might include several components, perhaps a heavy WIMP-like particle, along with some lighter axion-like particles, and even dark photons, hypothetical force-carrying particles for the dark sector. This hidden sector would be like a parallel world, influencing the universe only through gravity and maybe subtle quantum effects, which is why it has eluded detection. It's a bold idea, but it underscores how far scientists are willing to venture to explain the unseen majority of the cosmos. The truth could be stranger than any single simple candidate. Despite this zoo of possibilities, there are a few things we believe any dark matter candidate must satisfy. One is that dark matter should be cold, meaning its particles move relatively slowly compared to the speed of light. Cold dark matter clumps together and builds structures over time, matching the observed distribution of galaxies. If instead dark matter were hot, composed of particles zipping around at near light speed, it would have smeared out the small seeds of structure in the early universe, preventing galaxies, especially smaller ones, from forming as we see them. The success of our cosmological models, which reproduce the cosmic web and galaxy clustering, strongly suggests dark matter is cold and heavy enough to aggregate gradually. This narrows the field. Whether it's WIMPs, axions, or something else entirely, dark matter likely behaves as a slow-moving background of particles that began clumping early in cosmic history. In other words, it acts as a gentle but inexorable gravitational glue, allowing galaxies and clusters to form and stay intact. Indeed, cosmologists can measure how much dark matter exists by analyzing patterns in the cosmic microwave background and the way galaxies cluster on large scales. These measurements point to a universe composed of roughly 5% ordinary matter, the stuff of atoms, about 27% dark matter, and around 68% in an even more mysterious form of energy. In essence, for every star, planet, and gas cloud we see, that 5%, there is about 5 times more invisible mass lurking in halos around galaxies and in great cosmic filaments. This dark component had to be in place early, shaping the universe's evolution while remaining virtually undetectable except via gravity. Any viable dark matter candidate must fit these cosmic clues. It must have the right abundance, be cold enough to form the observed structures, and interact so weakly with normal matter that it leaves no obvious trace aside from its gravitational influence. The next step in unraveling the dark matter mystery is perhaps the hardest: finding it directly. It's one thing to infer the existence of this invisible mass from astronomical observations, and quite another to actually detect a dark matter particle here on Earth, or see unmistakable evidence of it in action. Yet across the world, physicists and astronomers have devoted themselves to this quest. The chase for the invisible is underway, using detectors deep underground, powerful particle accelerators, and dedicated observatories scanning the skies. Each approach is like a different net cast into the darkness, hoping to snare a passing shadow. Picture one of the world's most sensitive dark matter experiments. Deep in an old mine, a cavernous laboratory lies insulated by rock from the noisy world above. Inside, a giant tank filled with ultra-pure liquid xenon sits in almost total silence. Photomultiplier tubes line the tank, poised to detect a whisper of light. The hope is that a dark matter particle, after travelling unseen through space and through the Earth, might just happen to strike a xenon atom in this tank. It would be a tiny, subtle impact, like a ghostly billiard ball nudging another ball in the dark. Such a collision would produce a faint flash of light and a few drifting electrons, enough for the sensitive detectors to register amid the darkness. Experiments of this kind, there are several around the globe, have been running for years. So far, they have not caught a definitive dark matter particle. The detectors register only the occasional false hint from natural radioactivity or the rare cosmic ray that penetrates the shielding. Each time a potential signal appears, scientists scrutinize it, only to conclude it was something mundane. But importantly, these zero detections still advance our knowledge. With each year of data, physicists tighten the constraints on dark matter's properties. The latest generation of detectors has reached unprecedented sensitivity, enough to rule out whole classes of WIMPs that we once thought plausible. For instance, if robust WIMPs heavier than about 10 proton masses were common, we likely would have seen them bumping into xenon by now. The continued silence implies that if WIMPs exist, they must interact even more weakly than those early estimates assumed, or perhaps have masses outside the ranges we first anticipated. Essentially, the hunters have forced the quarry into an ever narrower corner of possibility. In the next few years, these experiments will become so sensitive that a new challenge looms. They will start picking up signals from something that is definitely real: neutrinos. Neutrinos are nearly massless particles emitted by nuclear reactions in the Sun and other stars. They stream through the Earth incessantly. Until now, our dark matter detectors have been mostly deaf to them, but as sensitivity improves, even neutrino interactions will register. This creates a kind of noise background that researchers call the neutrino floor, a point at which genuine dark matter events could be drowned out by a fog of neutrino signals. As we approach this limit, scientists are developing clever ways to tell a dark matter wink apart from the neutrino chatter, or designing future detectors that can circumvent the neutrino interference. There is a sense of urgency. The race is on to detect dark matter before hitting this fundamental wall of noise from the universe's most elusive ordinary particles. While some scientists listen for dark matter in quiet subterranean chambers, others have taken the opposite approach, creating the most energetic collisions on Earth to see if dark matter shows up. This is the strategy at the Large Hadron Collider, LHC, in Switzerland. When protons are smashed together at nearly light speed in the LHC's giant detectors, the hope is to produce exotic new particles, potentially including dark matter particles, from the energy of the collision. Of course, any dark matter formed would escape the detector unseen, like a phantom slipping through walls. But it would carry away energy and momentum. So physicists look for an imbalance in the collision debris. If, after a high-energy proton collision, it appears some energy is missing with no corresponding particle to account for it, that could be a hint that dark matter particles were produced and fled the scene. This technique is often referred to as a missing energy search. Over more than a decade of running, the LHC has yet to find clear evidence of dark matter. All the clever searches for missing energy or other telltale signs have so far come up empty. This null result, much like the underground experiment's silence, has progressively ruled out simpler ideas. Many straightforward supersymmetry models, for example, predicted a WIMP particle that the LHC should have created by now, yet nothing obvious has appeared. While disappointing in one sense, these results have been invaluable in guiding the field. By eliminating many possibilities, they steer theorists toward new ideas and push experimentalists to refine their methods. the LHC experiments continue to collect and analyze data at higher energies, and plans are underway for even more powerful colliders in the future. The pursuit of dark matter in the accelerator world is a long game, one that may yet yield a breakthrough with enough energy or a novel analysis of existing data. Meanwhile, astronomers scour the universe for any whisper of dark matter revealing itself through astrophysical phenomena. One strategy is to look for the byproducts of dark matter particles annihilating each other in space. If two dark matter particles collide, as might happen in the dense core of our galaxy or within ancient, dense clumps of dark matter, they could convert their mass into other particles, potentially a burst of gamma rays, high-energy light, or other detectable radiation. Telescopes like NASA's Fermi Gamma Ray Space Telescope have mapped the gamma-ray sky in detail, including the center of the Milky Way and dwarf satellite galaxies, which are thought to be especially dark matter-rich. There have been intriguing hints. A subtle excess of gamma rays at the galactic center that doesn't neatly match known sources, for example. For a while, some researchers wondered if this could be the glow of dark matter annihilation. But the picture is muddied by more ordinary explanations, such as populations of pulsars, rapidly spinning neutron stars that could produce a similar gamma-ray signal. At this point, no gamma-ray observation has definitively pointed to dark matter, only tantalizing puzzles that continue to be studied. Another observational approach focuses on stellar streams, lengthy trails of stars that orbit through the Milky Way, left behind by dwarf galaxies or globular clusters that were torn apart by tidal forces. These streams act like cosmic seismographs. As they drift through the galaxy's halo, any clump of dark matter they encounter can tug on them and kink or wobble the stream's path. By mapping these streams with precision, using data from missions like Gaia, which tracks the positions and motions of millions of stars, astronomers can infer where unseen masses lie, thus revealing how dark matter is distributed around us. Already, new surveys have revealed multiple stellar streams crisscrossing the sky, and subtle irregularities in their shapes that could be the footprints of invisible concentrations of mass. It's akin to seeing ripples in a river's flow and deducing there are rocks submerged under the surface. Using stars as tracers, this method, alongside gravitational lensing maps and cosmic background measurements, is giving us an ever richer view of the dark matter scaffolding enveloping our galaxy. As mysterious as dark matter is, scientists are grappling with an even more baffling invisible influence: dark energy. If dark matter is like an invisible scaffold holding galaxies together, dark energy is a phantom pressure pushing the universe apart. In the late 1990s, two independent teams of astronomers observed distant stellar explosions, type Ia supernovae, and made a shocking discovery. The supernovae were dimmer, and hence farther away, than expected, indicating that the expansion of the universe was not slowing down as everyone assumed, but actually accelerating. It was as if you tossed a ball upward, and instead of slowing and falling back, it began to speed upwards faster and faster. To explain this astonishing result, scientists invoked something completely new: an unknown energy imbued in the fabric of space, which they simply called dark energy. Ever since, dark energy has remained a placeholder name for whatever is driving the cosmic acceleration. We know it makes up about 68% of the universe's total energy content, and that it became dominant relatively recently, in cosmic terms, after the universe had already expanded and galaxies had formed. But beyond that, dark energy is as enigmatic as ever. For many years, observations were consistent with perhaps the simplest hypothesis: that dark energy is a cosmological constant, essentially a fixed, unchanging energy density associated with empty space itself. This idea actually dates back to Einstein, who first introduced a cosmological constant term in his equations of general relativity, then dropped it, thinking it was a mistake. In this model, dark energy does not evolve or interact. It's just a uniform feature of spacetime. If that's true, our universe will continue to expand faster and faster forever, leading to a distant future where galaxies outside our local group speed away beyond visibility, and the cosmos becomes cold and empty. To probe dark energy's true nature, scientists have been meticulously measuring how the expansion rate of the universe has changed over time. One approach is to use galaxies and quasars as markers on a cosmic timeline. The Dark Energy Spectroscopic Instrument, DSI, for example, has mapped millions of galaxies in 3D, creating the largest ever cosmic map and tracing the universe's expansion history back 11 billion years. Using 5,000 robotically positioned fibers on a telescope, DSI can gather light from a vast number of galaxies and precisely measure their redshifts, the stretching of their light due to cosmic expansion. In its first year of operation, DSI achieved better than 1% precision in measuring the expansion rate at multiple epochs between about 8 and 11 billion years ago. A remarkable feat that allows us to see subtle changes in the acceleration over cosmic time. So far, these detailed observations broadly support the standard lambda CDM model, a universe filled with dark matter and a cosmological constant. But there are hints of possible wrinkles. When DESI's early data were combined with other measurements, some analyses found that the simplest constant dark energy model might not fit perfectly. In late 2024, cosmologists reported tentative evidence that dark energy might be evolving, that it was slightly stronger in the past and has been weakening in recent epochs. If this is true, it would be revolutionary. It could mean that the acceleration of the universe is not a runaway process that will continue forever. Perhaps in the far future, cosmic expansion might even slow down again. Some have even speculated about a possibility in which dark energy could eventually reverse into attraction, causing the universe to collapse in a big crunch eons from now. We're not at that point by any means, but these ideas underscore how much is at stake in pinning down dark energy's behavior. At present, the evidence for evolving dark energy is not conclusive. The statistical confidence is not yet strong enough to claim a definite discovery. Many experts remain cautious, waiting for more data to say for sure. Still, the mere hint that dark energy might change over time has invigorated the field. After 2 decades of treating dark energy as a static mystery, we might be catching a glimpse of its dynamics. To further chase down the truth, new tools are on the way, or have just begun operation. In 2023, the European Space Agency launched the Euclid Space Telescope, a mission dedicated to exploring this dark universe. Euclid is surveying billions of galaxies across a huge swath of sky, measuring their shapes and how they cluster. From the subtle distortions in those galaxy shapes by invisible mass, weak gravitational lensing, and the pattern of galaxy clustering, Euclid will chart how structure formed under gravity and how dark energy influenced cosmic expansion over time. Meanwhile, on Earth, the Vera C. Rubin Observatory in Chile will soon commence the Legacy Survey of Space and Time, LSST, photographing the sky night after night with a giant wide-field camera. Rubin will discover vast numbers of distant supernovae, the same kind of standard candle explosions that first revealed the accelerating universe, allowing cosmologists to trace the expansion in great detail and watch for any shifts in dark energy's behavior. And later in the decade, NASA's Nancy Grace Roman Space Telescope will join the effort, with a wide-field survey optimized for both supernova measurements and gravitational lensing studies. Together, these projects promise an avalanche of new data. They are, in essence, a coordinated attempt to pin down the equation of state of dark energy, the ratio of its pressure to its density, and see if it deviates from the value of 1 that signifies a true cosmological constant. Amidst this, a curious discrepancy has emerged, known as the Hubble tension. Different ways of measuring the current expansion rate of the universe yield slightly different results. The cosmic microwave background, when interpreted with the standard model, implies one value for the Hubble constant, while direct measurements using nearby Cepheid variable stars and supernovae imply a higher value. This could be due to subtle issues with measurements, or it could be telling us that something in our cosmological model is missing. One hypothesis is that there was a bit of extra early dark energy in the universe a few 100,000 years after the Big Bang, just enough to affect the expansion rate before fading away. That could reconcile the conflicting measurements. It's speculative, but it highlights how mysterious dark energy is. It might have had phases or nuances to its behavior that we have yet to uncover. Solving the Hubble tension has become one of the major quests in cosmology, and it may well tie into the nature of dark energy or other new physics. As researchers chase dark matter particles in laboratories and dark energy's subtle effects in the sky, a few voices remind us to consider a more radical possibility. What if these invisible phenomena are not separate things at all, but signs of a deeper issue with our understanding of gravity and physics? Could it be that by adjusting our theories of gravity, we wouldn't need to invent unseen matter and energy to explain what we observe? It's a minority view, but worth contemplating. In the spirit of leaving no stone unturned, scientists have proposed modifications to known physics as an alternative to dark matter and dark energy. One prominent alternative to dark matter is the notion that our laws of gravity might need revision. If we could tweak the rules by which gravity operates on cosmic scales, perhaps we wouldn't need to invoke unseen mass. The most famous of these ideas is modified Newtonian dynamics, MOND. In the early 1980s, physicist Mordechai Milgrom proposed that Newton's law of gravity might not hold exactly at the extremely low accelerations found at a galaxy's outskirts. In MOND, when gravitational acceleration drops below a certain tiny threshold, gravity's pull doesn't fall off as quickly as Newton's inverse square law dictates. This tweak can naturally produce flat rotation curves for galaxies without dark matter, by effectively making gravity stronger on a galaxy's fringe than expected. With a suitably chosen acceleration scale, MOND indeed matches many spiral galaxy rotation curves rather well. However, MOND is not a complete theory by itself. It's more of an empirical prescription. Extending it into a full theory, compatible with Einstein's relativity, led to frameworks like TeVeS, tensor vector scalar gravity, which attempt to reproduce MOND effects in a relativistic context. Even so, modified gravity solutions face serious challenges. They can often explain the dynamics of isolated galaxies, but struggle with galaxy clusters and larger scale structures. The bullet cluster mentioned earlier is a case in point. In that collision of clusters, the gravitational lensing map shows mass in a different location from the visible hot gas, implying an invisible mass component that sailed through. A pure modification of gravity would have to contort itself to explain why the gravity in that system behaves as if mass were largely separated from the ordinary matter. Similarly, the pattern of minute temperature fluctuations in the cosmic microwave background strongly indicates a universe with a certain amount of dark matter to seed the formation of galaxies. No modified gravity theory so far has been able to account for every piece of evidence, from the rotation of galaxies to the layout of galaxy clusters to the imprint in the microwave background, in a simple, coherent way. It seems that even if gravity operates a bit differently on the largest scales, invoking some form of unseen mass still ends up necessary to explain all observations. Nevertheless, the exploration of such alternatives continues. Some theorists have explored ideas like emergent gravity, where gravity is not fundamental, but arises from deeper microscopic physics, perhaps linked to the entropy of quantum information. In one proposal by physicist Eric Verlinde, the equations of gravity in a universe with a lot of information, entropy, can lead to extra apparent gravity that might explain the missing mass problem without traditional dark matter. Early tests of this idea claim to reproduce galaxy rotation curves in a novel way, but it remains speculative and far from widely accepted. Other approaches tweak Einstein's theory itself. For example, so-called FR theories and other extensions of general relativity can produce effects similar to dark energy, effectively making gravity behave differently over vast distances. These modified gravity models can, in principle, induce cosmic acceleration without a true cosmological constant, or alter how structures grow in a way that mimics the presence of dark matter. However, when confronted with precision data, they often must be fine-tuned or end up reintroducing something that acts much like dark matter or dark energy to fit all the observations. The lambda CDM model's ability to match a wide array of data is a high bar for any alternative to clear. Alternate explanations for dark energy have also been explored. One idea is that perhaps we live in an exceptionally low-density region of the universe, a gigantic void, which could make distant galaxies appear to accelerate away from us more than they actually are. But detailed galaxy surveys don't support the existence of such an enormous void large enough to explain the observations. The acceleration seems to be a global phenomenon. Another approach posits a new, dynamic field, often dubbed quintessence, that fills space like a fluid with negative pressure. Unlike a true constant vacuum energy, this quintessence field could change slowly over time, causing the acceleration rate to vary. It's an appealing idea because it gives dark energy an evolving character, something we can potentially detect by observing different cosmic epochs. So far, however, our measurements of things like distant supernovae and the cosmic background have not conclusively shown any deviation from a constant dark energy behavior. Dark energy could be dynamic, but if it is, it changes only very subtly. The jury is still out, and that's why upcoming observations are so crucial. They may catch dark energy in the act of shifting, if indeed it does. Ultimately, the mainstream view still holds that dark matter and dark energy are real components of our universe, even if we don't yet know what they fundamentally are. Modified gravity or other exotic theories have not yet provided a simpler or more convincing explanation for the full range of phenomena we observe. But exploring these alternatives is important. It acts as a check on our assumptions and sometimes leads to new insights. Even disproving a bold alternative can deepen our understanding of why the prevailing theory works so well. In science, keeping an open mind goes hand in hand with rigorous testing. The invisible universe may have more surprises in store, and by examining every possibility, unseen particles, hidden forces, or adjustments to theory, we inch closer to the truth behind the phenomena that have so far defied our understanding. Our journey through this invisible universe is still in its early stages. We have traced the filaments of dark matter that weave the cosmic web and pondered the enigmatic push of dark energy. We have seen scientists laboring to detect the undetectable and even questioned the foundations of physics in search of answers. Yet the cosmos holds its secrets tightly. As we continue onward, we carry a sense of wonder and humility. There is more to uncover, just beyond our sight. The story does not end here. The exploration will flow onward, with the mysteries of the unseen universe guiding us forward, ever deeper into the cosmos's hidden realms. Imagine two immense clusters of galaxies, each containing hundreds of galaxies and enormous clouds of gas, hurtling toward each other at unimaginable speed. In the vast silence of space, these clusters collided in a cosmic ballet several billion years ago. The impact was one of the most energetic events since the Big Bang, releasing shockwaves and igniting the gas. When telescopes finally peered into this wreckage, they noticed something remarkable. The luminous clouds of hot, X-ray emitting gas had slammed into each other and slowed down under friction, heating up to tens of millions of degrees. Meanwhile, another component continued on its way. This striking event is now known as the bullet cluster, named after the bright bullet-shaped shock front visible in X-rays. The bullet cluster lies about 4 billion light-years away, so we see it as it was long ago. At the time of collision, the gas bullet was barreling through space at several thousand kilometers per second. Imagine something traveling millions of miles per hour through the cosmos, heated to tens of millions of degrees and glowing brightly. This colossal shockwave has been captured in X-ray imagery, appearing like a bright comet streak through the cluster. As the two clusters pass through each other, their components behave differently. Imagine two flocks of birds merging. The individuals rarely collide because the space is vast. In the same way, the galaxies within each cluster are so far apart that most flew by unaffected, as if passing through ghosts. The galaxies are like distant islands in an ocean, hardly noticing the other cluster's presence. However, the clouds of gas told another story. The gases make up most of the normal, luminous mass in clusters. These clouds clashed head-on with a tremendous shock. Charged particles in the gas collided and slowed down, heating the gas to tens of millions of degrees. In X-ray images, this collision is revealed by a bright, glowing bullet-shaped front, where the gas has been compressed. Meanwhile, an invisible substance kept moving. Dark matter does not feel the electromagnetic forces that slowed the gas. It feels only gravity. As a result, the visible gas was left behind in a glowing wake, while the unseen dark matter surged onward, largely unimpeded. Astronomers discovered this event by combining observations from multiple telescopes. The Chandra X-ray Observatory scanned the cluster in X-rays, highlighting the hot gas in brilliant detail. Meanwhile, optical telescopes like the Hubble Space Telescope and ground-based observatories photographed the galaxies themselves, pinpointing where they lay. Finally, by studying the subtle distortions in the shapes of even more distant background galaxies, they mapped the total mass via gravitational lensing. When the maps were compared, the result was astonishing. The bulk of the cluster's mass was centered around the galaxies, not the glowing gas. On the mass map, two massive clumps appear offset from the X-ray glow. These are the dark matter halos of the two original clusters, now leading the way. It was a clear sign that most of the mass was invisible. To uncover where the mass was, astronomers used a technique called gravitational lensing. They observed the distortions of light from galaxies far behind the collision. Gravity from the massive cluster warped and bent this light, as if the cluster was a cosmic lens. The pattern of distortion revealed where the mass was concentrated. It turned out that the areas bending light most strongly were not where the X-ray gas was glowing, but offset from it. Instead, the gravitational humps followed along with the galaxies and the invisible matter that had shot ahead. Two dark mass peaks aligned with the two galaxy clouds, indicating that each original cluster carried its own dark halo through the collision. It was a cosmic smoking gun. The majority of mass in the cluster lay in an unseen substance. This dramatic cosmic collision became one of the clearest proofs of dark matter's existence. It taught astronomers that most of the universe's mass is not made of the atoms in stars or gas, but of something unseen. The bullet cluster name itself comes from the glowing bullet-like shock of gas, but it's the unseen bullet of dark matter that left a lasting impression. In fact, galaxy clusters typically contain far more dark matter than normal matter. Only about 15% of the mass in such clusters is the glowing gas and stars we see. The remaining 85% is dark matter. In the bullet cluster collision, the visible part was just the tip of the iceberg. Astronomers effectively got to see the iceberg's outline. The luminous gas cloud was a small portion of the mass, while the ghostly dark matter, revealed by gravitational lensing, formed the much heavier part. It was as if the universe peeled back a curtain, showing the hidden mass behind the scenes. When this discovery was published in 2006, it sent ripples through the scientific community. Researchers around the globe pored over the data, stunned by the clarity of the result. Many hailed the bullet cluster as a smoking gun for dark matter. Suddenly, dark matter was not just an abstract idea. The collision had laid it bare. In lecture halls and popular articles, the bullet cluster became a favourite example and a striking image. Two glowing blobs, the gas, separated from the mass map, the dark matter. It showed that the unseen gravity we had long suspected was real and vastly dominant. Even years later, the bullet cluster is still a favourite example in astronomy education. It often appears in textbooks and documentaries as the most dramatic proof of dark matter. The image of its separated gas and mass distribution communicates the mystery of the invisible. To this day, it remains a cornerstone of evidence, a cosmic signpost pointing to unseen forces at work. With the bullet cluster, we saw clearly that our understanding of matter in the universe was missing a giant piece, the invisible dark matter that outweighs all the stars and gas. If one were to imagine the aftermath of the collision, it is instructive. The galaxies themselves continued on almost unaltered. Each galaxy remained accompanied by its own dark halo. In fact, gravitational lensing reveals two distinct blobs of mass, each aligned with one of the original clusters of galaxies. Each of these blobs corresponds to the dark matter halo of a cluster, now leading the gas. The individual galaxies are still there too, hundreds of them, acting like tracers of the two merging groups. This shows that even during such a violent event, galaxies can survive intact, held together by their own dark matter and stars. The bullet cluster did more than just confirm dark matter's existence. It taught us something about its nature. If dark matter particles collided with each other like gas molecules, they too would have slowed in the crash. The fact that the dark mass soared ahead, unimpeded, meant its particles barely interact with anything, including themselves. It was like two clouds of light, ghost, passing through each other. Scientists call this collisionless behavior. From this single cosmic smash-up, researchers learned that dark matter must consist of very elusive particles, not clumps or fluids that rub together. By analysing the collision, researchers set strict limits on how much dark matter particles can interact or slow each other down. In other words, this single cosmic crash taught us not only where dark matter was, but also how it must behave. Each model of dark matter now has to accommodate this ghostly, non-colliding character. For years, some scientists had tried to explain cosmic anomalies with changes to gravity itself, rather than unseen matter. The bullet cluster proved difficult for those ideas to match. Nothing in conventional physics could make the bulk of mass look like it was somewhere other than the glowing gas. This collision showed directly that the majority of mass is independent of the ordinary matter. In the quiet language of science, this clarity brought most researchers firmly onto the side of dark matter as the explanation. Subsequent studies confirmed that it was extremely hard to replicate these observations without adding dark matter. In many ways, this one cosmic event reshaped how scientists think about gravity and the cosmos. In the years since, astronomers have found several more merging clusters that show the same phenomenon. The bullet cluster remains the most famous, but it is not unique. Each new example reinforces the idea that galaxies carry along invisible companions when they collide. With every observation, the evidence for dark matter grows stronger. Each one is like another ghost, showing the same traces where matter exists beyond sight. Throughout cosmic time, dark matter has played the role of an unseen architect. It silently assembled the first galaxies and guided the formation of clusters. It wove a vast web across the universe, connecting structures across millions of light years. Dark matter made the cosmos what it is, rich with galaxies, stars, and planets. Without it, the universe would be a far emptier place. Even now, every galaxy we see traces its shape to this hidden scaffolding. Its presence is marked only in the motions of stars and in the bending of light, for it does not glow or shimmer. This grand story of structure has its roots in the earliest times after the Big Bang. In those first moments, the universe was an almost uniform sea of particles and radiation. Tiny irregularities in density, like ripples on a cosmic pond, were present even then. Unlike ordinary matter, dark matter did not interact with the hot plasma of photons, so it began to clump under gravity even earlier. When the universe was about 380,000 years old, it cooled enough for atoms to form and light to travel freely. The afterglow, known as the cosmic microwave background. The patterns in this ancient light tell us about the small fluctuations in density at that time. Crucially, those fluctuations could not grow as observed without the gravitational pull of dark matter. Dark matter provided the additional mass that helped amplify those slight irregularities. From the moment the first light spread across space, the universe's structure already bore the marks of dark matter's influence. Satellites like WMAP and Planck have since mapped this ancient light in exquisite detail. The ripples in the cosmic microwave background match what we would expect, only if most of the matter then was invisible dark matter. From those observations, scientists infer that roughly 5 out of every 6 matter particles were dark. This confirms the same story. Even in the universe's baby photos, dark matter was the architect. In time, those tiny irregularities grew under gravity. Dark matter's extra pull drew ordinary matter toward the denser regions. As the universe aged, vast structures began to emerge from the once smooth soup. Computer simulations of the expanding cosmos reveal a complex network, the cosmic web, composed of long filaments and sheets of dark matter. Dark matter formed the unseen framework on which galaxies and clusters would later assemble. The gas and dust that could cool and form stars fell into these gravitational wells. Slowly, the first galaxies flickered to life, tracing the dark skeleton beneath. In this way, dark matter guided the formation of every galaxy and cluster. The night sky's familiar stars sit within galaxies that owe their existence to this invisible scaffolding. Computer simulations of the Big Bang tell a similar story. Starting with the conditions measured in the cosmic microwave background, scientists run supercomputer models of cosmic evolution. These simulations only reproduce the filamentary cosmic web of galaxies and clusters if dark matter is included. Indeed, the largest simulations, simulating billions of years in minutes, show galaxies clustering along vast networks of dark matter. Without dark matter in the equations, the universe they produce would be nearly empty. Take our own Milky Way as an example. We see a beautiful spiral of stars, nebulae, and dust. But this luminous disk is only part of the story. All around the galaxy is a vast halo of dark matter, invisible yet overwhelmingly massive. The stars, the glowing arms, and even the gas together have much less mass than this dark halo. In fact, the Milky Way's dark matter halo could extend hundreds of thousands of light years beyond the visible disk. Within this unseen cocoon, smaller satellite galaxies and gas clouds orbit, bound by its gravity. This invisible halo exerts the majority of the gravitational pull in our galaxy. It is the dark skeleton that holds the Milky Way together. Every galaxy, from the smallest dwarfs to the largest giants, sits inside a similar dark cocoon. Even clusters of galaxies are held together by massive halos of dark matter. When astronomers map the three-dimensional distribution of galaxies in the universe, a web-like pattern emerges. Clusters and superclusters line up along the same filaments predicted by simulations of dark matter. These observations reaffirm how deeply dark matter is woven into cosmic evolution. For instance, surveys like the Sloan Digital Sky Survey have plotted the positions of millions of galaxies, revealing an intricate cosmic web. Where simulations expect dense knots and threads, the real universe shows galaxies piled up in just those regions, with vast voids in between. This correspondence between theory and reality shows that the gravitational pull of dark matter guided the growth of all these structures. Modern measurements of the cosmos confirm how dominant dark matter is in cosmic evolution. When scientists weigh all the matter and energy in the universe, only a small fraction is made of atoms. By contrast, roughly a quarter of everything is in dark matter. This means that ordinary matter, the stars, gas, and dust, is just a tiny minority. Dark matter is about 5 times more abundant than normal matter. Every galaxy, every cluster, forms within this vast reservoir of unseen mass. In essence, the universe grew up inside a cocoon of dark matter. Understanding the grand architecture of the cosmos means understanding this invisible scaffolding. Dark matter did not act only on one scale, it worked hierarchically. Small clumps of dark matter merged into larger ones over billions of years. Each merger formed more massive halos that could gather even more matter. For instance, our Milky Way likely formed from the merging of many smaller galaxies, their dark halos combining. Clusters of galaxies formed at the intersections of these merging filaments, becoming the giants of the cosmos. In this cosmic game of building blocks, dark matter always provides the glue. Thanks to dark matter's scaffolding, the first stars and galaxies could appear relatively quickly after the Big Bang. Observations show galaxies already formed when the universe was only a few 100 million years old, implying rapid collapse of gas in dark halos. These early galaxies lit up the cosmos and rayonized the surrounding gas. Without dark matter providing those deep wells to trap the primordial gas, the dawn of stars and galaxies might have been delayed much longer. Even the smallest galaxies tell of dark matter's role. Dwarf galaxies, with only a few million stars, nonetheless seem to be dominated by dark matter. When astronomers measure how fast stars orbit in these dwarfs, they find speeds that require far more mass than the visible stars alone. In fact, some of these faint galaxies appear to be almost entirely dark. It's as if dark matter cloaks these tiny islands of stars. Dark matter's gravitational pull was first noticed much closer to home, in individual galaxies. When Vera Rubin and others measured the rotation of spiral galaxies, they found that the outer stars were moving far too fast to be held by the stars and gas we see. This implied that each galaxy must be embedded in a much more massive halo of unseen matter. The same dark substance that prevented stars from flying off galaxies is the very same that we see directing galaxies to their places in the cosmic web. In that sense, dark matter connects the scale of a single galaxy all the way up to the web of clusters. Throughout cosmic time, dark matter has played the role of an unseen architect. It silently assembled the first galaxies and guided the formation of clusters. It wove a vast web across the universe, connecting structures across millions of light years. Dark matter made the cosmos what it is, rich with galaxies, stars, and planets. Without it, the universe would be a far emptier place. Even now, every galaxy we see traces its shape to this hidden scaffolding. Its presence is marked only in the motions of stars and in the bending of light, for it does not glow or shimmer. This immense influence raises a central question. What exactly is dark matter? If it shapes the universe, what is it made of? Answering that question will take scientists back down to Earth and into deep underground laboratories. It will open a new chapter of mystery, the search for the elusive nature of dark matter itself. The search for dark matter's true identity has led scientists to some of the quietest places on Earth. Deep underground, beneath kilometers of rock, they have carved out laboratories shielded from interference. In these vaults, enormous detectors wait in silence. Some are filled with ultra-pure xenon, others with supercooled germanium or liquid argon. The idea is simple. If a dark matter particle whizzes through, it might occasionally collide with an ordinary nucleus. Such a collision would deposit a tiny burst of energy. The detectors are built to spot exactly that. In essence, these scientists are listening for a nearly imperceptible tap of the invisible on the visible. Experiments seeking dark matter particles come in many designs. Some use supercooled crystals of germanium or silicon, watched by ultra-sensitive sensors. Others fill large chambers with noble gases like xenon or argon in liquid form. For example, the Lux Zeppelin LZ experiment uses 7 tons of liquid xenon deep underground in the United States, while the Xenon in T detector in Italy has over 8 tons. In each case, scientists watch for a tiny flash of light or a jitter in an ionization signal, the possible sign of a dark matter particle striking a nucleus. Even the faintest glow is examined carefully. To reduce interference, these detectors are surrounded by layers of shielding and sensors to veto cosmic rays. Every detail is pushed to the limit to catch an exceedingly rare event. For decades, the search for dark matter has only deepened the silence. Major experiments filled with liquid xenon, like Lux Zeppelin LZ in the United States and Xenon 1T in Italy, report no candidate events. Other detectors, such as Panday X in China and DarkSide in Italy, likewise see only background noise. Even a long-running experiment in Italy named Dharma, which claimed a slight annual signal, has not been confirmed by independent groups. With each null result, the possible properties of dark matter particles are further constrained. Physicists respond by building ever larger, more sensitive detectors. The planned Darwin Observatory, for instance, would use on the order of 50 tons of liquid xenon to probe interactions many times weaker than before. Despite all this effort, the detectors remain tuned to silence. Astronomers have also turned the sky into a laboratory. They search for the fingerprints of dark matter, annihilation, or decay. If dark matter particles occasionally collide or decay, they might produce flashes of gamma rays, neutrinos, or other particles. The Fermi Gamma Ray Space Telescope has mapped the center of our galaxy, a region expected to be rich in dark matter. Some analyses find a faint, unexplained glow in gamma rays there, but the signal could also come from many unknown pulsars. That clue remains too subtle to be certain. Neutrino observatories like IceCube in Antarctica and Antares in the Mediterranean listen for high-energy neutrinos from the Sun, where dark matter could accumulate and annihilate. They have found no clear excess beyond expectations. Other experiments scan cosmic rays for anomalies. The Alpha Magnetic Spectrometer on the International Space Station, for example, measures cosmic rays to look for signs of dark matter. It has observed curious patterns in positrons and antiprotons, but these too can be explained by known sources like pulsars or supernovae. In short, the universe continues to withhold definitive evidence. Its whispers remain ambiguous. High-energy physics experiments have joined the hunt too. At CERN's Large Hadron Collider, protons are smashed together at near light speed, hoping to create exotic new particles. If a dark matter particle were produced in those collisions, it would escape the detector unseen, hinting at its presence through missing energy and momentum. Over many runs and trillions of collisions, the LHC experiments have found no clear sign of dark matter. Every time, the data match the predictions of known particles. Each null result pushes theorists to adjust their models. If dark matter is at the LHC's energies, it must be more elusive than expected. But for now, the LHC serves mostly to narrow down the possibilities. Researchers have also explored very different candidates. Some theories propose that dark matter could be an ultralight particle called an axion. Experiments like the axion, Dark Matter Experiment, ADMX, use strong magnetic fields and sensitive radio receivers, trying to convert passing axions into detectable microwaves. So far, these searches have not found axions either, but they continue to scan through possible mass ranges. Other ideas, like dark matter, being small black holes, or sterile neutrinos, have become less favoured as observations tighten their constraints. In effect, the simplest and more obvious candidates have been tested and eliminated. Yet another reminder that the truth is still hidden. Despite these frustrations, the hunt for dark matter continues with even greater resolve. New, larger detectors are being built. Upcoming experiments will use many tons of ultra-pure liquids and more advanced technologies, sensitive to even tinier signals. Scientists work to eliminate every bit of background noise that might hide the truth. It is a bit like turning up the volume on a cosmic radio, hoping to hear a faint station that has so far eluded us. Patience and ingenuity keep researchers pushing forward. With each null result, they refine their understanding and the search strategy. The silence persists, but it is a silence that will not last forever. As detectors become ever more sensitive, they even begin to register neutrinos. Neutrinos from the Sun, or cosmic rays, occasionally collide in the detectors, creating signals that could be confused with dark matter. Future experiments will soon reach the so-called neutrino floor, where neutrino interactions become a background that is hard to beat. At that point, distinguishing a dark matter signal will require new strategies. This is a reminder of how faint dark matter's signature must be. Scientists have also considered more exotic candidates. One possibility is that dark matter is made of axions or other very light particles. Experiments like ADMX and CAST search for axions by looking for their conversion into photons in strong magnetic fields. These setups use ultra-sensitive radio receivers or crystal detectors, hoping to see faint signals at specific frequencies. So far, no telltale photon has been caught, but the searches are ongoing. Axions could be far lighter and more weakly interacting than WIMPs, so they require very different detectors. In a way, the dark matter search has expanded to cover the entire spectrum, from heavy WIMPs down to ghostly axions. As results keep coming in, physicists sometimes question whether dark matter is what we think. Could we be looking in the wrong place? Some wonder if the solution might come not from a particle, but from a hidden principle of physics. For example, modified gravity theories attempt to explain observations without dark matter. But so far, nothing has matched all the facts as neatly. For now, the leading idea is still that dark matter is a type of particle we have yet to observe. It might be a whole new kind of matter that interacts only very weakly. The mystery remains wide open. While dark matter itself remained hidden, the cosmos had another secret to tell. A decade ago, astronomers peering at distant supernovae discovered that the expansion of the universe is actually speeding up, not slowing down as expected. This revelation hinted at a new mystery, something pushing the galaxies apart with a mysterious force. In the quiet halls of dark matter experiments, scientists took note, knowing that their journey through the invisible cosmos had much more to reveal. At the end of the 20th century, astronomers found a startling truth written in the stars. Two separate teams, racing to measure the universe's expansion, turned their telescopes to distant exploding stars called Type Ia supernovae. These stellar explosions are so bright, they serve as cosmic mileposts. When the researchers compared how fast those far-off galaxies were receding to how bright the supernovae appeared, they expected to see the expansion slowing under gravity. Instead, the data told a surprising story. The expansion of the universe was speeding up. In other words, something was pushing the galaxies apart with ever-growing force. Those observations came as a shock. Scientists had expected the cosmic expansion to slow down under gravity's pull. They compared the redshift of distant supernovae with their brightness as predicted by deceleration. But to their surprise, the faraway supernovae appeared dimmer than expected. It was as if the expansion had accelerated. In science, this was a revolution. When those results emerged, they were confirmed by an array of data. In 2011, the leaders of the supernova teams, Ries, Schmidt, and Perlmutter, shared the Nobel Prize in Physics for this discovery. It made clear that dark energy was not a fluke, but a real force in the universe. From that point on, unraveling dark energy became a central goal of astronomy. What could cause this cosmic push? The simplest explanation is that empty space has energy of its own. This idea dates back a century to Einstein's cosmological constant, originally introduced and then discarded in relativity theory. If space itself is infused with energy, it would exert a gentle repulsive pressure. That pressure is invisible yet pervasive. In effect, the cosmos carries with it a mysterious energy density that does not dilute as it expands. Physicists label this unknown influence dark energy. It acts like a tiny anti-gravity, significant only on the largest scales, but over billions of light years, it dominates the universe's behavior. Subsequent observations reinforce the case. The cosmic microwave background measurements, like those from the Planck satellite, point to a flat universe. This implies there must be more energy filling space than matter alone accounts for. Galaxy surveys have also uncovered a baryon acoustic oscillation signature, a subtle rippling pattern in galaxy clustering that also points to the same cosmic recipe. When scientists combined the supernova results with the cosmic background measurements and galaxy surveys, the conclusion was inescapable. Dark energy comprises about 70% of the cosmos. All evidence fits an accelerating universe with that composition. To put it another way, imagine the total contents of the universe as a pie. Roughly 7 slices out of 10 would be dark energy, and only about 1 slice out of 20 is made of familiar atoms. Everything we see, stars, gas, planets, and ourselves, resides in that thin, ordinary sliver. Dark matter accounts for most of the rest, and dark energy fills the lion's share. This cosmic pie chart shows how dominant dark energy has become, even though it remains the most elusive portion. By 2011, the importance of this discovery was clear. The leaders of the 2 supernova teams, Ries, Schmidt, and Perlmutter, received the Nobel Prize in Physics for finding that the universe's expansion is accelerating. This recognition underscored that dark energy was now a fundamental piece of the cosmic puzzle. A vast effort followed. Ground-based telescopes like the Subaru and the European Very Large Telescope hunted more supernovae. New space missions like ESA's Planck measured the cosmic background in finer detail. Together, they painted a consistent picture. Despite all this evidence, the nature of dark energy is still a mystery. It could be Einstein's cosmological constant, a fixed energy density of empty space, or it could be something more exotic, like a new dynamical field pervading the universe. Physicists often parameterize its effect by a number W, which measures how its pressure relates to its energy density. A value of W equals 1 corresponds to a constant vacuum energy. So far, observations indicate W is very close to 1,1, with no clear sign of change. If future measurements find W differs from 1,1 by even a small amount, it would upend the simple constant model. Some theories propose dark energy could slowly vary over time or transform, but none are confirmed. For now, dark energy acts like a truly constant presence, its influence growing as space stretches. The universe has become a stranger place than anyone expected. In uncovering dark energy, we have opened a door to new mysteries. Looking ahead, the dominance of dark energy guides our expectations for the cosmos's fate. If it remains constant, the universe will keep expanding at an accelerating rate. Galaxies not bound to us will speed away, eventually disappearing from view. The sky would gradually darken as stars burn out. However, if dark energy changes with time, other scenarios are possible. Some hypothetical models predict a big rip, where dark energy grows so strong that it rips apart galaxies, stars, and eventually atoms themselves. While such an outcome is speculative, it illustrates how dependent our cosmic destiny is on understanding dark energy. For now, most evidence points toward a gentler future where space keeps stretching forever. To unravel this mystery, astronomers have mounted ambitious observational campaigns. Projects like the Dark Energy Survey and future space missions such as Euclid and the Nancy Grace Roman Telescope are mapping the universe with exquisite detail. They measure the expansion history by observing distant supernovae, galaxy clustering, and gravitational lensing. In the coming years, many dedicated projects will deepen our understanding. The Dark Energy Spectroscopic Instrument, DSI, on a ground telescope will measure the distances of tens of millions of galaxies. The Vera C. Rubin Observatory, formerly LSST, will image billions of galaxies every few nights, allowing precise mapping of cosmic expansion. Each of these surveys is designed to test whether dark energy is truly constant or if it evolves. Meanwhile, space missions like ESA's Euclid and the Nancy Grace Roman Telescope will measure supernovae, galaxy clusters, and weak gravitational lensing with unprecedented accuracy. They will investigate whether the laws of gravity might vary over cosmic distances. By combining their results, scientists hope to finally illuminate the nature of dark energy. In the quiet of the night sky, the universe is still whispering its riddles, waiting for us to listen deeper. In the silent darkness of intergalactic space, a long-held assumption quietly began to unravel. Astronomers had believed that the combined gravity of all matter, both the ordinary kind and the unseen dark matter, would gradually slow the expansion of the universe. The cosmos, they thought, should be decelerating as galaxies tugged on one another, their mutual gravity putting the brakes on cosmic growth. But as the 20th century drew to a close, a series of observations hinted at a stunning twist in the cosmic story. Instead of slowing down, the expansion of the universe appeared to be speeding up. To probe the fate of the cosmos, astronomers in the 1990s set out on an ambitious quest. Two independent teams of researchers, one based in California, the other spanning institutions around the world, aimed to measure the expansion rate of the universe over cosmic time. They knew that if gravity had been slowing the expansion, the evidence would be written in the sky. The plan was elegant: find and observe distant exploding stars as cosmic yardsticks, and use them to chart the universe's expansion history. On those observing runs, the researchers searched patiently for these cosmic signposts. They compared photographs of the night sky taken weeks apart, looking for tiny points of light that suddenly appeared. A supernova igniting in a distant galaxy. Whenever a new supernova was found, telescopes around the world and in space swung into action to measure its brightness and spectrum. Each of these stellar explosions, occurring billions of light years away, carried a message from the past. By capturing their light, scientists were, in essence, seeing the universe as it was billions of years ago, and measuring how fast it was expanding back then. On one clear night, for instance, astronomers poring over their telescope images spotted a faint new pinprick of light in a distant galaxy, a supernova that had suddenly flared into view. That exploding star was so far away that its light had been travelling for billions of years, long before Earth even formed. It arrived as a tiny flicker on a computer screen, carrying a message from the universe's past. When they calculated the supernova's distance and compared it to its redshift, they found it was dimmer than expected, a telltale hint that it lay farther away than it should in a slowing universe. It was as if the ancient star's dying light had stretched extra far, revealing that the expansion of space had sped up while that light was en route. One by one, such supernova beacons told the same story, each reinforcing the reality of a runaway universe. The exploding stars they relied on were Type Ia supernovae, titanic stellar detonations that briefly outshine entire galaxies. Crucially, these supernovae have a known intrinsic brightness. Like standard candles placed at known distances, Their true luminosity serves as a cosmic ruler. By comparing how bright a distant supernova appears to its known actual brightness, astronomers can determine its distance. And by measuring the redshift of the supernova's host galaxy, the stretching of its light due to the expansion of space, they can gauge how much the universe has expanded since that star's light began its journey. With distance and redshift together, it becomes possible to trace the expansion rate at different epochs of the universe. For decades, scientists had debated the ultimate fate of the universe. Would gravity eventually triumph, slowing the expansion to a halt and pulling everything back into a big crunch? Or would the cosmos continue to expand forever, coasting outward eternally, but ever more slowly as the eons passed? The answer depended on how much matter the universe held to fuel gravity's pull. By the late 1990s, with powerful new telescopes at their disposal, astronomers were finally poised to find out. If the expansion had been decelerating, the distant supernova measurements would show it. Night after night, the teams gathered light from distant supernovae and carefully analyzed their brightness. As the data accumulated, a puzzling trend emerged. The far-off supernovae appeared slightly dimmer, and thus farther away, than expected if the universe's expansion had been slowing normally. At first, the researchers wondered if something was misleading them. Could interstellar dust have made the supernovae appear fainter? Or might those distant explosions somehow differ from nearby ones? They checked and rechecked their work, seeking any mistake that could explain the strange result. But no error was found. The dimness of the distant supernovae was genuine, and its implication was astounding. The expansion of the universe was not slowing at all. It was accelerating. In 1998, both teams announced this astonishing discovery. The universe, they revealed, is expanding faster now than it was in the past. What should have been a gentle slowing of cosmic expansion under gravity's influence had turned into a cosmic speed-up. The assumption of a gradually breaking universe was shattered in one stroke. The scientific world was stunned. Decades of thinking about the universe's fate were suddenly upended by this single revelation. This unexpected finding was soon hailed as the breakthrough of the year, and in the years that followed, the astronomers who uncovered cosmic acceleration earned the highest honors in science. The term runaway universe began to circulate, a vivid description of a cosmos racing away unchecked. It was as if the cosmos had slipped out of gravity's grasp, raising profound new questions about what force could be behind this runaway expansion. One way scientists conveyed the shock was with a simple analogy. Imagine tossing a ball upward and seeing it not fall back, but shoot higher and higher, faster and faster. That is how unexpected the accelerating universe was. Something unseen was propelling everything apart. In time, astronomers gave this mysterious agent a name: dark energy. An invisible energy now seemed to permeate space, pushing galaxies outward and overwhelming gravity on the largest scales. The discovery of this dark energy marked the beginning of a new chapter in cosmology, one filled with mystery and wonder at the unseen forces shaping our fate. Incredibly, the notion of a cosmic repulsive force was foreshadowed long before dark energy became a mystery. Over 80 years earlier, Albert Einstein had introduced a peculiar concept into his equations of general relativity: the cosmological constant. This term acted like a built-in anti-gravity effect, a mathematical force that made empty space push outward. Einstein added it because he, like many scientists of his era, believed the universe was static and eternal. His cosmological constant provided just enough outward pressure to counterbalance gravity and hold the universe in a steady state, neither expanding nor contracting. At the time, Einstein's revolutionary equations of gravity suggested that a static universe was unlikely. Without some extra repulsion, gravity would make the cosmos collapse in on itself, or conversely, a lack of enough gravity would let it expand unchecked. Uncomfortable with those implications, Einstein chose to fine-tune the universe with the cosmological constant. This term, denoted by the Greek letter lambda, L, represented a fixed energy embedded in space itself, effectively a gravity of empty space that could oppose ordinary gravity. In essence, Einstein created a theoretical form of dark energy decades before we knew to call it that. One can imagine Einstein in the late 1910s, sitting at his desk, wrestling with the implications of his newly formulated gravity theory. The equations in front of him suggested an unthinkable scenario, a dynamic universe that refused to stand still. At that time, the very idea of an expanding or contracting cosmos felt implausible. After all, no one had observed galaxies rushing apart, and the Milky Way was thought to be the entire universe. Determined to preserve a static cosmos, Einstein introduced the cosmological constant. In his mind's eye, this extra term was like a subtle mist filling all of space, a gentle pressure to counteract gravity and hold the universe in balance. For a while, that addition provided peace of mind. The universe could remain eternal and unchanging, as he and many others believed. Little did he know that this mathematical tweak, born of philosophical preference, would boomerang back into relevance decades later, after evidence of cosmic expansion came to light. Not all of Einstein's contemporaries were convinced that this cosmic counterweight was needed. In the 1920s, physicists like Alexander Friedmann and astronomer Georges Lemaitre found that Einstein's original equations, without the constant, naturally permitted an expanding universe. They suggested that the cosmos might be stretching from an initial explosive beginning. Einstein, however, was skeptical. He reportedly dismissed Lemaitre's work as flawed, unwilling to abandon the comforting idea of a stable cosmos. For him, the cosmological constant remained a necessary fix, until observational evidence proved otherwise. That evidence arrived in 1929, when Edwin Hubble discovered that galaxies are flying away from each other, revealing that the universe is indeed expanding. Upon hearing of Hubble's findings, Einstein is said to have sighed and conceded that the cosmological constant was no longer needed. He dropped the term from his equations. In later recollections, physicist George Gamow claimed that Einstein called the cosmological constant his biggest blunder, a colourful admission that adding that repulsive term to force a static universe had been a mistake. For the next several decades, Einstein's lambda seemed to be an unused footnote in cosmology. The universe was expanding without any known need for a mysterious anti-gravity force. Cosmologists shelved the cosmological constant and focused on matter and gravity to explain cosmic behavior. Yet, unbeknownst to them, that blunder would resurface. When the acceleration of the universe was discovered in 1998, scientists quickly realized that Einstein's forgotten idea could be the key. A small but positive cosmological constant, essentially a persistent energy woven into the fabric of space, would naturally cause cosmic expansion to speed up over time. Reconsidering Einstein's term, theorists found that it fit the new data astonishingly well. This renewed cosmological constant is now the simplest explanation for dark energy. In Einstein's equations, it behaves as a uniform energy density filling space, exerting a repulsive influence on large scales. As the universe grows and matter thins out, this uniform energy, lambda, doesn't dilute. Its relative influence increases, pushing galaxies apart ever more effectively. A positive, tiny lambda could precisely account for the runaway expansion observed in the modern universe. Today, this idea has become a pillar of the standard cosmological model. In fact, the model is often named lambda CDM. Lambda for the cosmological constant, dark energy, and CDM for cold dark matter. According to this model, dark energy, as a manifestation of Einstein's lambda, makes up roughly 2/3 of the total contents of the cosmos. Far from being a blunder, Einstein's once abandoned constant now appears to capture an essential truth about our universe, that empty space itself carries a hidden energy. It is a profound irony that Einstein's revision to his theory, made to preserve a static universe, turned out to foreshadow the dynamic reality of cosmic acceleration. His cosmological constant has been vindicated, but the story doesn't end there. Even if dark energy is this constant energy of the vacuum, we are left with deep questions. Why does this energy exist? Why is it so small, yet so dominant? And is it truly constant, or could it change with time? In seeking answers, scientists are delving into the nature of dark energy itself, the mysterious force driving the expansion, which we will explore next. The term dark energy is a deliberately vague name for a very real phenomenon. It labels whatever unknown influence is causing the expansion of the universe to accelerate. Dark simply means we cannot see it and do not yet understand it, and energy indicates that it behaves like a form of energy woven into the fabric of space. In truth, dark energy is a kind of placeholder for our ignorance, a convenient shorthand for whatever is pushing the cosmos apart. We know it's there from its effects, but we don't yet know what it actually is. What do we know about dark energy? For one, it appears to be smoothly distributed, not clumped into galaxies or clusters. Unlike matter, whether normal or dark energy doesn't gather in one place. It seems to be a property of space itself. It also has a peculiar effect on gravity. Rather than pulling things together, it drives them apart. In essence, dark energy acts like a kind of negative gravity or repulsive pressure on cosmic scales. This is the opposite of dark matter, which pulls with gravity but emits no light. Dark matter binds galaxies, while dark energy pushes galaxies away. Through various measurements, scientists have inferred that dark energy currently makes up about 2/3 of the total contents of the universe. It dominates over all the matter in the cosmos. This was not always the case. In the early universe, matter was denser and gravity reigned supreme, slowing the expansion. But as space expanded and matter thinned out, dark energy's influence grew. Roughly 5 billion years ago, dark energy overtook matter as the dominant component, and the expansion began speeding up. Today, dark energy defines the large-scale behavior of the cosmos. It's a humbling thought that nearly 70% of the universe is made of this dark energy, utterly unlike the matter and light we know. Imagine looking out into a clear night sky. For all the billions of stars and galaxies we can see, the true dominant ingredient of the cosmos is invisible. The galaxies themselves, magnificent as they are effectively just glittering foam on a vast, dark sea of energy. This realization has transformed our perspective. In a way, dark energy has made the universe feel larger and more mysterious than ever. A reminder that, despite our great strides, we are still children in the cosmic dark, trying to understand an overwhelming and unseen presence. Yet for all its dominance, dark energy remains an enigma. It doesn't emit or absorb light. We can't bottle it in a lab or poke it directly. All we have are hypotheses, and they range from the straightforward to the mind-bending. The simplest explanation, as touched on earlier, is that dark energy is a cosmological constant, an unchanging energy of empty space. In other words, the very vacuum of space might contain energy that produces a repulsive force. This idea aligns with Einstein's old cosmological constant, now resurrected, to explain the accelerating universe. If this is true, then every cubic centimetre of space hums with a tiny amount of energy that never goes away. And as the universe expands, new space brings more of this energy into existence, causing the expansion to push outward ever more forcefully. Such vacuum energy has a basis in quantum physics. According to quantum theory, even empty space seethes with ephemeral particles flitting in and out of existence. This quantum vacuum might have an intrinsic energy. And indeed, in quantum field theory, empty space is not truly empty, but filled with fields and virtual particles. In principle, this vacuum energy could act exactly like Einstein's cosmological constant, driving space to expand. However, when physicists attempt to calculate the vacuum energy from fundamental theory, the numbers don't match reality at all. The theoretical predictions often overshoot the amount of dark energy we infer from astronomy by an enormous factor, many orders of magnitude too high. On the other hand, certain theoretical arguments can cancel out the energy almost entirely, yielding virtually zero. Neither extreme comes anywhere close to the tiny but non-zero dark energy that the universe actually exhibits. This huge discrepancy between theory and observation is known as the cosmological constant problem, and it underscores just how far we are from comprehending this mystery. If dark energy isn't a simple constant of nature, perhaps it changes over time. Some scientists have proposed the idea of quintessence, a new dynamic energy field pervading the cosmos. Quintessence, named after the ancient concept of a fifth element, wouldn't be fixed like a cosmological constant. Instead, it could vary in space and time, increasing or decreasing in strength as the universe evolves. Unlike a constant vacuum energy, quintessence would be more like a fluid or field with its own properties, potentially clumping slightly or interacting in subtle ways. If this were true, dark energy might have been weaker in the past, or might change in the future, which could alter the fate of the universe. So far, observations have not clearly detected any variation in dark energy, but the search for signs of quintessence continues. Others have explored more exotic possibilities. One idea is that what we call dark energy might stem from unusual cosmic relics. For instance, hypothetical defects in space-time structure left over from the Big Bang. Imagine imperceptible wrinkles or topological features stretching across space like invisible threads, sometimes termed cosmic strings or domain walls. These could, in theory, affect the expansion of the universe, producing a dark, energy-like effect. This concept is speculative, but it shows how creative scientists are getting in, trying to explain the accelerating cosmos. There is also a camp of researchers attacking the dark energy problem from another angle entirely. What if our theory of gravity itself needs revision? Perhaps Einstein's general relativity, brilliant as it is, might not tell the whole story on the scale of the entire universe. Some modified gravity theories can produce an accelerating expansion without requiring a new energy component at all. For example, by tweaking how gravity works over vast distances, these theories try to account for the observed acceleration as a gravitational phenomenon rather than an exotic energy. So far, none of these alternative theories has garnered convincing evidence to unseat dark energy. but they serve as a reminder that we may yet need new physics to understand what's happening. In sum, dark energy could be a constant energy of space, a dynamic fluid-like field, an effect of hidden cosmic defects, or a sign of new gravitational physics, or something we haven't even thought of yet. Each explanation comes with challenges. The cosmological constant fits the data, but confounds theory with its tiny value. Quintessence and other fields are intriguing, but so far indistinguishable from a constant in observations. Exotic ideas like cosmic strings or modifications of gravity remain speculative. For now, astronomers and physicists use the cosmological constant as a working model for dark energy, because it is simplest and seems to agree with all current measurements. What is clear is that dark energy is one of the greatest puzzles science has ever faced. It touches on deep questions of quantum physics, space-time, and the ultimate fate of the universe. Solving this mystery will likely require breakthroughs in both observation and theory. As one researcher quipped, understanding dark energy might demand a new Einstein, a revolutionary idea or discovery that changes our fundamental picture of reality. In the meantime, scientists around the world are actively devising experiments and observations to probe dark energy's effects more precisely, hoping to glean clues about its true nature. By observing how the universe expands and structures grow under dark energy's influence, we inch closer to answering the question, what is this shadowy energy that rules the cosmos? If dark energy is mysterious, the evidence for its existence is now overwhelming. The accelerating expansion, initially revealed by supernova observations, has since been corroborated by a wide range of cosmic measurements. Over the past decades, multiple independent tests, from the afterglow of the Big Bang to the distribution of galaxies, have all pointed to the same startling conclusion. An unseen force is at work on the grandest scales, making the universe expand faster and faster. One linchpin of evidence comes from the cosmic microwave background, CMB, the faint microwave glow left over from the Big Bang. Satellites like NASA's WMAP and the European Planck mission have mapped the tiny temperature ripples in the CMB across the sky. These ripples encode information about the universe's composition and shape. The data indicate that the universe is spatially flat, meaning its total energy density balances out the curvature of space. However, when astronomers add up all the known matter, both normal and dark matter, they only get about 30% of the needed density. The remaining 70% must be something else. That something matches perfectly with the inferred amount of dark energy. In other words, the CMB measurements strongly imply that most of the cosmos is made of dark energy, even though the CMB itself comes from a time long before dark energy dominated. By including dark energy in their models, scientists can explain the precise patterns in the CMB. Thus, the CMB provides an independent, early universe confirmation that an unseen energy component is woven into the universe's fabric. Another powerful clue lies in the large-scale clustering of galaxies. Surveys such as the Sloan Digital Sky Survey and more recently the BOSS and DESI projects have mapped the positions of galaxies in 3 dimensions. They detected the subtle imprint of primordial sound waves, known as baryon acoustic oscillations, BAO, in the cosmic web of galaxies. This imprint provides a standard length scale, a ripple in the galaxy distribution about 500 million light-years in size, set by processes in the early universe. by measuring how the apparent size of this ripple changes with distance, and thus look back time. Astronomers can trace the history of cosmic expansion. These studies find that the BAO scale has grown in a way that indicates accelerating expansion. In essence, the very pattern of galaxies on the sky carries the fingerprint of dark energy's push. The agreement between the supernova results and the BAO results is striking. Both methods, completely independent of one another, point to the same conclusion. The universe's expansion is speeding up, and a new ingredient, dark energy, is required to explain it. This concordance gives us added confidence that we're on the right track in understanding the cosmic acceleration. The distribution of galaxy clusters, enormous congregations of hundreds of galaxies bound by gravity, also provides evidence. Galaxy clusters grow over billions of years. Their abundance at different epochs depends on the competition between gravity and expansion. If gravity were unchecked, clusters would keep forming, growing ever larger. If expansion accelerates, it impedes cluster growth. Observations using X-ray telescopes, which measure the hot gas within clusters, and optical surveys, which count clusters, show that the growth of clusters slowed down in the latter half of cosmic history. This is exactly what we expect in a universe where dark energy took over and began accelerating the expansion. The number of massive clusters observed at various distances fits well with models that include dark energy, further confirming its reality. In short, the tally of galaxy clusters through time acts like a cosmic accounting ledger, indicating when and how strongly dark energy has influenced cosmic structure formation. Even the way light itself travels through expanding space offers clues. As the universe accelerates, the light from distant objects is stretched more than it would be otherwise, and the gravitational influence of massive structures on light is altered. Astronomers have observed a phenomenon called the integrated Sachs-Wolf effect, a slight change in the CMB photon's energy as they pass through large clusters of galaxies, which occurs only if the expansion is accelerating. Additionally, weak gravitational lensing surveys, which map how intervening mass warps the shapes of background galaxies, find that the clumping of matter on large scales is somewhat suppressed relative to what it would be without dark energy. This subtle signal aligns with predictions. An accelerating expansion reduces the growth of structure. All of these observations, from the way light gains or loses energy traversing clusters to the delicate stretching of galaxy images, reinforce the picture of a cosmos under the influence of dark energy. By the mid-2000s, cosmologists had a concordance model that unified all these observations. The supernovae, the CMB, the galaxy clustering, cluster counts, and other tests all pointed to a universe in which approximately 68% of the energy is dark energy, about 27% is dark matter, and only 5% is normal matter. This model, lambda CDM, has become the standard framework. It's remarkable that a single set of numbers can match such a diverse array of data, from the brightness of distant supernova to the temperature fluctuations of the CMB. It gives scientists confidence that, however strange dark energy is, we are measuring its effects correctly. Having established that dark energy is real, the next step is to measure it even more precisely and discern its properties. Is dark energy truly constant in time, as a cosmological constant would be? Or are there hints that it changes or interacts, as more exotic theories predict? To answer these questions, a new generation of experiments and observatories is coming online. One of them is the European Space Agency's Euclid mission, launched in 2023. Euclid is creating a 3D map of the universe by surveying billions of galaxies up to 10 billion light-years away. From this vast map, scientists will extract the expansion rate at different cosmic ages and the pattern of how structure has grown, both key imprints of dark energy's influence. Another eagerly awaited observatory is NASA's Nancy Grace Roman Space Telescope, slated for launch by the late 2020s. Roman will have a field of view 100 times larger than Hubble's, with similar resolution. This will allow it to conduct massive surveys of galaxies and discover thousands of new supernovae out to great distances. By observing these supernovae, Roman will tighten the measurements of how the expansion rate has changed, potentially catching any slight deviations from a perfectly constant dark energy. Roman will also use techniques like weak lensing and galactic redshift surveys to independently measure the distribution of matter and the geometry of the universe, further pinning down dark energy's effects. On the ground, the Vera C. Rubin Observatory, formerly LSST in Chile, will soon begin its deep survey of the night sky. Rubin's legacy, survey of space and time, is designed to repeatedly image the entire visible sky, catching transient events like supernovae and tracking changes over a decade. Rubin will unveil unprecedented numbers of distant supernovae and provide detailed maps of how matter, through gravitational lensing, is distributed. This wealth of data will help determine whether the acceleration is changing over time or if new anomalies emerge. In addition, projects like the Dark Energy Spectroscopic Instrument, which is measuring millions of galaxy redshifts, and other international surveys are contributing vast amounts of information to this effort. Looking further ahead, other innovative approaches are on the horizon. NASA's upcoming Sphere-X mission, for example, will survey hundreds of millions of galaxies across the sky in infrared light, searching for patterns that could relate to dark energy's early influence. Scientists are even considering how future gravitational wave observations might serve as standard sirens to independently gauge cosmic expansion. The combined onslaught of data from these initiatives will help test whether dark energy behaves exactly like a cosmological constant, or if there are slight wrinkles that could tip us off to new physics. We stand at the dawn of what has been called a new golden age of cosmology. The mystery of dark energy, once a shocking revelation, is now driving an entire field of research. Day by day, telescope by telescope, we are mapping the influence of this invisible energy with greater clarity. Each piece of evidence, every distant supernova captured, every pattern traced in the cosmic microwave background, every galaxy mapped, is another clue in the ongoing investigation. For cosmologists, this truly feels like standing on a new frontier. Each new telescope and survey is like launching a fresh voyage into the unknown. With every deep observation, we extend our reach further, tightening our grasp on dark energy's elusive parameters. There is a quiet exhilaration in this work, knowing that somewhere in the vast volumes of data, a subtle clue might be waiting, a hint that could finally reveal what dark energy is. Until that moment, scientists continue scanning the skies, patient and hopeful, gathering light from across the universe to piece together the story of this invisible force. Yet, despite the tremendous progress in measuring dark energy's effects, its true identity remains elusive. We find ourselves in the curious position of knowing that our universe is dominated by something we scarcely understand. For now, dark energy is a name on our equations and a series of effects in our observations. In time, those observations may guide us to a breakthrough in physics that reveals what dark energy really is. As we continue this cosmic journey, we are not only learning about dark energy, we are also pushing the boundaries of knowledge, challenging our theories, and deepening our appreciation of how astonishing the universe truly is. The story of dark energy is still unfolding. In the next part, we will delve deeper into what these invisible forces, dark matter and dark energy, mean for the fate of the cosmos and our understanding of reality. The universe's unseen influences have led us this far, and they hold the key to even greater discoveries ahead. Our exploration of the invisible universe continues as we seek to illuminate the darkness with the light of scientific insight. Having wandered among galaxies and glimpsed the influence of dark matter, we now drift into the vast emptiness itself. Far from any stars or galaxies, in the silent vacuum of space, an invisible energy hums. Space itself seems to have a substance, a subtle pressure pushing outward on the cosmos. Scientists have discovered that around 68 to 70% of the universe's total energy is this dark energy, unseen but felt across the vast emptiness. It is an energy born not of matter or light, but of space itself. Though it is called dark, it is neither fully understood nor directly observed. We only know that it is causing the universe to expand faster over time. Astronomers sometimes picture the vacuum as alive with quantum flickers. Even empty space is thought to shimmer with pairs of particles and antiparticles that briefly appear and cancel out, filling each point with a tiny amount of energy. This vacuum energy behaves like a constant pressure, not attractive like gravity, but repulsive. If we could see it, the vacuum might appear to undulate with this subtle energy, like a calm sea with hidden currents. In fact, Albert Einstein himself introduced what we now call the cosmological constant in his equations. He added it so the universe could be static, balancing gravity with a repulsive term. When Edwin Hubble later showed that space is expanding, Einstein reportedly called the constant his biggest blunder. Now physicists wonder if that once dismissed term was prescient. Perhaps it truly represents the vacuum's energy driving today's acceleration. In Einstein's theory of gravity, both energy and pressure shape the cosmos. Normal matter and radiation have positive pressure and tend to pull space together. Dark energy is thought to have a large negative pressure, meaning it pushes space apart. One can imagine the vacuum as if it was stretched like a rubber sheet under tension. This counterintuitive repulsive effect is what drives the accelerated expansion we observe. What does vacuum energy actually imply? Calculations should tell us, but they don't match reality. Quantum theory suggests empty space has energy, and plugging in all known fields gives an outrageously large number. Naive predictions overshoot the observed value by about 10 to 120. An amount so huge that the early universe would have blown itself apart long before stars could form. This mismatch has been noted for decades. Yakov Zeldovich was among the first to apply quantum mechanics to this problem. In 1967, he found that vacuum fluctuations imply an enormously large cosmological constant. In practice, however, the observed vacuum energy is tiny by comparison, an extraordinary fine-tuning that remains unexplained. Remarkably, dark energy's dominion began only in the last few billion years. Earlier on, the gravitational pull of matter was stronger, and the universe's expansion was actually slowing down. Then, roughly 5 billion years ago, dark energy's repulsion overtook gravity, and the expansion started accelerating. Why this cosmic balance happened now, just as observers like us have emerged, is a mystery, sometimes called the cosmic coincidence problem. Scientists can only shrug at this timing, noting it as one more clue in the story. Careful observations have cemented this picture. Surveys of distant supernovae showed the expansion was speeding up. Measurements of the cosmic microwave background and the large-scale distribution of galaxies also match a universe made mostly of dark energy. All this evidence points to a cosmos 3/4 full of this mysterious vacuum energy, even though we still do not know its true identity or origin. Some scientists suspect that dark energy may not be constant at all, but something more mysterious. What if this energy evolves over cosmic time, rather than remaining fixed? This idea opens the door to a variety of exotic possibilities. One leading concept is quintessence, in which dark energy arises from a new field filling space. Quintessence would act like a fluid with negative pressure that can change strength. Unlike a simple constant, it could grow stronger or weaker over the eons as the universe ages. Theoretical models often treat quintessence as a slowly rolling scalar field, akin to the inflation field of the early universe, whose energy density evolves with time. Scientists have searched for any sign that dark energy might be changing this way to gain clues to its nature. Some theorists even contemplate a more extreme form: phantom energy. In phantom models, dark energy's repulsion grows without bound, driving the equation of state parameter below 1. This would spell a violent end called the Big Rip, where gravity is not just overcome, but overwhelmed. Phantom fields require exotic physics, even allowing negative kinetic energy, and remain highly speculative. So far, no observations demand W1, but the possibility has motivated scientists to keep an open mind. Another exotic idea comes from the early cosmos. In the universe's youth, phase transitions could have left behind defects in space, filaments or membranes stretching across the cosmos. Examples include cosmic strings or domain walls. These would be like wrinkles frozen into spacetime, relics of high-energy physics. If such defects exist, their tension and energy could contribute a repulsive effect on large scales. In this view, dark energy might be a kind of built-in quirk of the cosmic fabric. However, no clear evidence of these space wrinkles has emerged yet, so this idea remains speculative. Perhaps dark energy means there is no new substance at all, but rather a flaw in our understanding of gravity. Some theories extend Einstein's general relativity so that gravity behaves differently over cosmic distances. One class, called FR gravity, adds extra curvature terms to the equations. Another, brain world models, imagines our universe as a membrane in higher dimensions that subtly changes gravitational strength. In these cases, the observed acceleration arises from modified gravity rather than an unknown energy. Researchers have even revisited Einstein's old ideas about alternative formulations of gravity and how cosmic expansion might be explained without dark energy. So far, general relativity has passed every test, and alternative gravity theories must be carefully designed to match observations. Scientists search for telltale deviations, for example in the way galaxies cluster or how light bends over the largest scales, that might reveal a departure from Einstein's laws. So far, none of these alternatives has been confirmed. Observations are consistent with dark energy behaving like a perfect cosmological constant. Measurements have constrained its equation of state parameter to be very close to 1, with no significant signs of change. Any quintessence or modified gravity model must closely mimic a constant dark energy to fit the data. Future observations will continue to sharpen these constraints, looking for even the slightest hint of deviation. In short, a wide menagerie of ideas remains alive. Dark energy might be a simple cosmological constant, a changing field, a space-time defect, or a sign that gravity behaves oddly at large scales. Each scenario carries its own implications. As one expert put it, the enormous discrepancy between theory and observation tells us that there's something missing in our story. For now, observations are the ultimate arbiter, and the simplest explanation remains consistent with the data. But until dark energy's true nature is revealed, all these possibilities will be explored by researchers hungry for answers. Some theorists even invoke the multiverse to explain the puzzling value of dark energy. In this view, our universe is one of countless others with varying physical constants. Perhaps only in universes where dark energy is tiny can complex structures like galaxies and life form. We then find ourselves in such a lucky cosmos, and the why now problem is answered anthropically. This idea remains speculative, but it reflects how strange the dark energy problem is. On more speculative fronts, some scientists explore the idea that dark energy might arise from yet unknown quantum effects, or the structure of spacetime. One recent proposal suggests vacuum fluctuations polarize space, giving rise to a small effective energy. Others have suggested entropic or information-theoretic origins, where gravity and expansion emerge from thermodynamic principles. These ideas are still emerging, but they underline how dark energy touches upon the deepest questions of physics. Dark energy has profound consequences for the cosmos's destiny. If the repulsive push of dark energy continues or grows, the expansion will simply speed on forever. In a constant dark energy model, galaxies drift beyond view and star formation eventually ends, leading to a cold, empty future. A more extreme possibility, if dark energy strengthens, is the so-called Big Rip, where even galaxies, stars and atoms are eventually pulled apart. These fates are far off in time, but they hinge on how dark energy behaves now and into the future. In this scenario, galaxies gradually drift apart like ships on an endless ocean. In just a few 100 million years, clusters of galaxies beyond our local group will move out of sight. About 1 trillion years from now, the gas needed to make new stars will be exhausted, and the night sky will grow ever darker. Existing stars will burn out one by one, leaving behind dim remnants, white dwarfs, neutron stars, and black holes. As time marches on, even the faint glimmers of stellar light will fade. Deep into the far future, all orderly structures will be gone. Eventually, the universe will be left only with cold remnants, fundamental particles, radiation, and perhaps a thin gas of neutrinos, all extremely spread out. Entropy will have reached its maximum, and nothing new can happen. This bleak fate, called the heat death, is where the cosmos remains in eternal stasis. The second law of thermodynamics tells us that a system evolves toward greater disorder, and the universe is no exception. In effect, the cosmos will become a vast, cold emptiness, uniformly quiet everywhere. Another, more dramatic possibility is the so-called Big Rip. If dark energy grew increasingly strong over time, its repulsion could eventually overwhelm all forces binding the universe. In that scenario, distant galaxies are torn apart first, then the Milky Way, the solar system, and finally, atoms and subatomic particles. Space itself would fracture, leaving only empty vacuum. We have no evidence that this extreme outcome will occur, and it would happen only if W1, Current data push any potential big rip into a far distant future, if it occurs at all. Of course, this story depends on dark energy never changing course. If, hypothetically, dark energy were to wane or disappear, gravity might take over again. In that case, the expansion could slow and reverse, possibly leading to a big crunch. However, all current evidence suggests the expansion will continue accelerating. For now, the most likely future is a quiet fade out, with the universe growing ever colder and emptier. Ultimately, dark energy sets the stage for whatever future unfolds. Whether the universe gently cools into darkness or tears itself apart, the outcome depends on the invisible force we are just beginning to understand. Each scenario is based on extrapolating today's unknown dark energy into the far future. For now, we can only say that our cosmic destiny is bound to the fate of this dark energy, even as we continue searching for answers about its true nature. Astronomers observe dark energy through its effect on the cosmos. One of the most powerful probes has been exploding stars known as Type Ia supernovae. These serve as standard candles. By measuring their brightness and redshift, scientists can map how the universe's expansion has changed over time. It was precisely this supernova technique that revealed the accelerating expansion in 1998, a discovery honored with the 2011 Nobel Prize. Ongoing supernova surveys keep refining our picture of cosmic acceleration. Other clues come from mapping cosmic structure. Galaxies are not scattered randomly. Their clustering carries the imprint of sound waves from the early universe, baryon acoustic oscillations. By surveying galaxy positions over billions of years, instruments like the Dark Energy Survey and the Dark Energy Spectroscopic Instrument trace the expansion history. Even the cosmic microwave background, the relic light from the Big Bang, provides vital information. Measurements of its fluctuations by satellites like Planck fix the early universe's conditions, which in turn demand about 70% of the cosmic energy to be in dark energy today. Astronomers also use the subtle bending of light by gravity to study dark energy. Massive clusters of galaxies distort the images of background galaxies, and by measuring these weak lensing effects, we can infer how structure growth has slowed under cosmic acceleration. Future missions, like the Euclid satellite and the Nancy Grace Roman Space Telescope, will map billions of galaxies in 3D to trace dark energy's influence. On the ground, the Vera Rubin Observatory, formerly LSST, will survey the sky night after night, refining measurements of supernovae, galaxies, and lensing. Together, these projects promise unprecedented precision in watching the universe's expansion accelerate over time. All these methods mark the beginning of a new golden age of cosmology. With ever more powerful telescopes and surveys, scientists are collecting data of unprecedented detail. Year by year, our measurements of cosmic expansion and structure become more precise, bringing us closer to unveiling the nature of this dark force. Even after decades of study, the essential nature of dark energy remains a mystery. We still don't know what it truly is, whether it's vacuum energy or a dynamic field or something new beyond our current understanding. We've measured its presence, but its value and behavior remain unexplained. The cosmological constant problem, why its measured energy density is so small compared to theoretical expectations, stands as one of physics' greatest puzzles. Is dark energy truly constant, or could it evolve imperceptibly over time? Current observations have constrained its equation of state to be very close to 1, meaning it appears constant for now, but any slight change could betray new physics. To find out, scientists measure the universe's expansion across the largest scales and smallest effects. They track motions of hundreds of millions of galaxies and the faint distortion of distant galaxies by weak lensing. Each new survey sharpens our picture. In parallel, laboratory tests and gravitational wave observations are pushing the boundaries of gravity to see if dark energy's secret can be unveiled. Some argue it may simply be a fundamental constant of nature, with its value a numerical coincidence. If so, perhaps there is no deeper explanation. Others find that unsatisfying. The problem remains a puzzle worth pursuing. In the end, dark energy stands as one of the great mysteries of modern physics, awaiting new clues to guide our understanding.